Impressionnez les employeurs avec un CV professionnel de CV.fr et distinguez-vous de tous les autres. Créez votre CV simplement en 3 étapes. Remplissez vos coordonnées, sélectionnez un modèle professionnel et téléchargez votre CV. Essayez-le dès maintenant.
Please, please. Dominic. Who's Dominic? Dominic is here. Bejembo. Charlotte Diatta. C'est Gaye. Ah, c'est Gaye. Ah, d'accord, ok. C'est bien là? Cheikhouna Gaye. Ok, Cheikhouna Gaye, ok. Cheikhouna Gaye, donc à Bejembo. Amadou Ibrahima Mbaye. Amadou Ibrahima ay Diatou. We are start the first session. What is the man who must present in the first session? First session. I think you two. You are two. You are this man and this one. Okay.
Hello, good morning, everybody. Good morning. Good morning. Could you settle down? Thank you. Thank you. We are now starting. Could you please go to page 19 of your program? Could you please go to page 19 of your program? Hello, good morning, everybody. Bonjour. Bonjour, madame. Could you please go to page 19 of your program? Yes, on page 19, we have 5 presenters. 5 presenters. The first one is isolation and microbial activities of novel, discolonide, and other compounds. That is S4C38. Are the authors here? Clarence Medina, are you here with your co-authors? If Clarence is not here, could number 39 step up? Bidai Mobile, Mame Kumdiop. Are you here? Optimization of extraction conditions by the dosage. You see here?
Same.
Yes.
Oh, okay.
Anybody for page 19 here, step up so you can present. It's S4, C40, anti-hyperglycemic effect of Sheffield or immune derivatives. Are you here? S4C41, rapid identification of antioxidants in ethanolic and aqueous extracts of mangrove trees. Yes? Yeah.
Sorry, I think the ones you are calling should be for the order of digital. This is Adasonia. It should be page here. This is digital. Probably they are in the...
Please, error. No. Recall? Where's Neil? I believe we're on page.
Mistake. No. Why? No. Here is a 10. It's a mistake. You can hear it's 19. Here you are one session. There are two rooms. This room. We are mistake.
You gave me night.
Mistake.
Okay, where's your?
Other is we are the same room. 2 sessions, same room. Here is good.
Is digital also?
And down.
Yes. Where is this room?
This room is Adoniza is mistake here.
Okay, the room number, the name, the room is mistake. So it's
here.
It's Adasinia that is here.
After I go down, I call the Marcia one for one.
So these people are downstairs waiting.
Are we?
These people, they've gone downstairs.
Yeah.
So you have to go downstairs
I go
to bring them up.
Here. Yeah.
Okay.
Exactly.
So is this man downstairs? Yes. Is this man?
This man is missing.
He's not here.
No, he's not here.
Okay.
Takes his place.
Which one is yours?
Rapid notification. Yeah.
I go down. I go down. I bring.
Load. It's before you. Should you load?
I go
Okay.
down. I bring some water.
Okay. Hello. There's a typographical error. Page 19 is supposed to be this hall. It's a typographical error. As such, some of the presenters may be downstairs, thinking they're supposed to be downstairs. When they come, they'll make their presentation. The first presenter for us today will be Mbo, that is S4C39, optimization of extraction conditions by dosage. Please, you have the floor. That's for 15 minutes.
Please. Okay. Okay, thank you very much. Thank you, President. Ladies and gentlemen, I'm so proud to be here to present our communication oral. The context is 6 annual days of chemistry of Senegal and 9th FAST Congress, FAST Jazz 2024. The title of our communication is Optimization of Extraction Conditions by the Dosage of Polyphenol and Determination of Antioxidant Activity. Case of Melothria madrespatana organs, a plant used in traditional African medicine for the treatment of diabetes. This work was carried out in the laboratory, Groupe de Recherche sur les Substances Bioactives, Department of Chemistry, University Cheikh Anta Diop. As an introduction, the plant is man's friend for his survival, providing him with food and medicine since the earliest times of civilization. For a long time, they have been a valuable source of natural products to maintain human health, especially in recent decades with more intensive studies on natural therapies. This picture shows a medication car. Nowadays, the use of phytochemical of pharmaceutical purpose has gradually increased in many countries. Specifically, current research has shown that Melothria is a good source of natural and effective antioxidants such as polyphenol. The aim of this work is to evaluate the polyphenol contents and the antioxidant activity and optimal extraction from the leaves of Melothria madrespatana. In fact, traditional practitioners prescribe medication without taking into account the contents. For example, this picture shows a traditional practitioner shop where bags and bottles are offered to the population without dosage or therapeutic indication scientifically verified. The work developed here will provide a beginning of an answer to the problematic. And our methodology is without optimization of Melothria madrespatana extraction parameters. Temperature, time, and solvent constitute a determining factor to the extraction of secondary metabolite in plant material samples, as well as for the determination of their biological activity. Temperature, first. In order to determine the optimal temperature, the extraction is done with 0.5 grams of plant material distilled water at different temperatures for some times in a water bath. Second of time, once the optimal temperature is determined, The optimal extraction time is the next parameter. We set the temperature and the extraction mass and vary the duration. Third, of solvent, the temperature and duration having been determined, the variation of the quantity of plant material to be extracted of distilled water is carried out to determine the optimal extraction ratio. And the antioxidant activity was determined by the DPPASH method. The content polyphenol compounds was determined with the Folin Seocalt region, and the flavonoid contents was calculated by the method described by Dürer and al. We go to present the result and discussion. The first parameter is temperature, and this curve shows evolution of total polyphenol contents and DPPASH antiradical activity as a function of temperature. This curve shows that the polyphenol contents reach his first maximum at 80 degrees, at 70 degrees. And during this time, the activity antiradical decrease. At 90 degrees, the content of polyphenol reached his second max. And during this time, the activity antiradical increased. At 80 degrees, the polyphenol content and the activity tends towards these maximum values. Allow us to take this value of maximum optimal condition extraction. The second parameter is the time. At 30 minutes, we can see that the polyphenol contents and the activity reach these maximum values. And beyond this value, the polyphenol contents and the activity decrease. And we can take this value as the optimal condition of extraction. And the third parameter is solvent ratio, solvent volume. If we look the curves, we can see that at 1 gram, the total content polyphenols and the activity reach this maximum value. And beyond this value, these two parameters decrease. And we can take this value as the optimal condition expression. In conclusion, we can see that the result obtained illustrated in the 3 previous figures reveals that the total polyphenol contents and the antioxidant activity from leaves of this plant are optimized by dissolving 1 gram in 5 milliliters of plant material for a period of 30 minutes and a temperature of 80 degrees. After determining these optimal conditions, we go to the application of these conditions in the aqueous extract of all the plant organs. And this diagram shows the contents of polyphenol, flavonoid, and the quantity of antioxidant DPPASH in this condition. Temperature 80 degrees, duration 30 minutes, and ratio 1 gram in 50 milliliters of solvent. And the result obtained show a significant flavonoid content in the leaves of Melothria madrespatana, twice as high as that in the stems and fruits. Compared to polyphenol, we notice a balanced distribution in the 3 organs of the plant, with an average value of 5 milligram by gram of extract. Further, the stems constitute the most active part for DPPASH, slightly higher than the aqueous extract of the leaves and fruit. In conclusion, we can say that the total polyphenol contents and the antioxidant activity of Melothria are optimal by dissolving 1 gram in 50 milliliters of plant material for a period of 30 minutes and at a temperature of 80 degrees. Moreover, the 3 parts of the plant have very interesting total polyphenol and flavonoid contents with significant antiradical activity compared to the reference. In perspective, we can say that a more complete phytochemical study is in perspective in order to evaluate the antimicrobial and anti-cancer activities up to the isolation and characterization of the bioactive molecule content is found. Thank you for your attention. Okay, thank you.
May I call on the next presenter to step forward?
No.
We have Dr. Gay to make this presentation, rapid identification of antioxidants in ethanolic and aqueous extracts of mangrove trees from Senegal using a specific coupling method.
Merci. Hello everyone. My name is Shakhuna Gay, and I will present to you a method for coupling UHPLC, HR, MS, and DPPAH used in our laboratory. It is a coupling that makes it possible to detect compound with antioxidant activity in a complex mixture such as plant extract. So first of all, this work is part of my thesis, which is valorizing the plant species from Senegalese mangrove by using an ethnopharmacological approach, because these species are widely used in traditional medicine. However, there are a few studies carried out on their pharmacological properties. And then the aim of this work that we are going to present today is therefore to study one of the pharmacological properties, that is the antiradical activity by using the DPPH method. So in the mangrove in Senegal, we find 6 plant species, three species from the Rhizophoracea family, that is Rhizophora mangal, Rhizophora racemosa, and Rhizophora racemosi, Rhizophora arizoni, and 1 species of the genus of Avicennia germinans, and 2 species for the family of Combretaceae, that is Conocarpus erectus and Lagunicularia racemosa. So, and after identification of these species, we use the different parts of this plant, and we made 2 forms of extracts: hydroethanolic extract by percolation, and aqueous extract by decoction, which is the method used in traditional medicine. So after this extraction, we have 24 extracts. These extracts are used for the study of antiradical activity by DPPH method. First, the principle of this antioxidant test is based on the absorbance reduction of the DPPH radical in the presence of antiradical compound. So DPPH is a radical with maximum absorbance at 517 nanometer. It transforms into yellow DPPH. It is the form reduce of DPPH radical in the presence of antiradical compound, which results in absorbance reduction. So to study the antiradical properties of our species, we will first work in a 96 well plate. Once filled with calibration range, the plates are placed in the plate reader. So after 1 hour of incubation, at 20 degrees, the absorbance is measured at 517 nanometer. And then percentage of inhibition is calculated, which subsequently makes it possible to determine the personal inhibition curve as a function of concentration. The 50% personal inhibitory concentration is determined. That means that the antioxidant concentration necessary to reduce 50% of the initial radical DPPH. So the result is grouped in this chart. So in blue we have the inhibitory concentration for aqueous extract, and in green we have the inhibitory concentration for ethanolic extract. From this, we therefore excuse me. The result, from this, we therefore set activity threshold. There is therefore an extract is considered active if inhibitory concentration is lower 20 microgram per milliliter, and moderately active between 20 and 50, and the extract is considered inactive above 50 microgram per milliliter. So we use active extracts for the second part of this study, that is the DPPH online. So this coupling consists of firstly using UHPLC and DID chain for separation, and then after the outlet of the column, a portion of the separate analyte react with a DPPH solution in continuous flow in a reaction call. And the endocyne decoloration is detected as a negative peak by a visible detector at 517 nanometer. The other part of the analyte separate is analyzed by a mass spectrometer running in negative ionization mode. The mass data obtaining for this time is allowed to the annotation for active metabolites. So it looks like this. Here we have an example, a molecule routine. At the top we have the UV chromatogram, and below we have the negative peak, which represents a reaction with DPPH reaction. And then we can therefore make connection with mass spectrometry data and determine the compound responsible for the antiradical activity. So if you use our extract, so for the hydroethanolic extract of Lagunicularia racemosa leaf, one of the species in this study with high antioxidant activity, we have four compounds which are mainly responsible for the antiradical activity. And so, in using mass spectrometry data, we will be able to annotate the four compounds. So first, for the first compound, we use the mass spectrum for determining the molecule formula using the database. Donc first we determine the mass molecular and the molecular formula, and then after we use the fragmentation data for identification for this molecule. And after comparison with a literature, I find experimental spectra of this molecule to see if we have a correspondence of the spectra or not. So after comparison with literature spectral data, we have found this molecule is identified as a gallowil bis hexahydroxydiphenyl glucose. This is the first compound we have identified for this method. So we do the same method for the third other compound, and the second compound is identified as quercetin, and the third compound is identified as myricetin, and the fourth compound is identified as quercetin. In result, we saw the first compound responsible for anti-radical activity of this extract. It is the extract of ethanolic extract of Lagunicularia racemosa leaf. Donc we saw the fourth compound who's are responsible for this activity, anti-radical activity. For the aqueous extracts of the same species, Lagunicularia racemosa, we identified two compounds, isoquercetin and gallowylbis hexahydroxydiphenyl glucose. And then when we make connection of these two extracts, also hydroethanolic extract and aqueous extract, we saw there are two common compounds, gallowylbis hexahydroxydiphenyl glucose and isoquercetin for these two extracts. So, and this, we have another extract, the ethanolic extract of Conocarpus erectus leaf. We identified three molecules. First, it is a phenolic molecule, ellagic acid, myricetin and quercetin, and two molecules is currently being identified. So we have found the molecule formula, but we continue to identify the name of this molecule. Here we have the aqueous extracts of the same species, so the Conocarpus erectus leaf, and here we have identified two molecules, ellagic acid and myricetin, and one molecule who is currently being identified. So here we have another extract who have an activity, an anti-radical activity. This is ethanolic extract of Rhizophora mangle, and here we have two molecules, two compounds or two metabolites who is responsible of this anti-radical activity. It is rutin first, and in two we have quercetin opaque fumaroyl hexazide. And here we have the ethanolic extract of Lagunicula of Rhizophora racemosa, excuse me.
So I noticed that there were themes
we have the extract, ethanolic extract of Rhizophora racemosa leaf. It is you have one compound who is responsible of
keeping
this
it light
activity.
or having something
it is
that
rutin
gives you
molecule.
energy. Oh, I realized.
And here we have make a connection for three extracts of the family of Rhizophoraceae, the aqueous extracts leaf of Rhizophora mangle, Rhizophora racemosa, and Rhizophora arisoni. And here we have one molecule, rutin, common molecule rutin, who have responsible of this activity. So this method is very rapid and permit us to identify. It is the first time to identify a molecule of this plant species of mangrove in Senegal. And it is the first time also we study the pharmacological activity of plant species of mangrove in Senegal. So thank you.
Thank you very much for your presentation. Two questions. Or comments? Thank you very much.
Merci.
May I call on SC4C, SC4, S4C38, isolation and antimicrobial activities of novel, disclonide, and other compounds from monad ataxis discolor. Professor Clarence A. Megina. Could we please encourage him?
morning, everybody. Today I will be presenting the findings that we had on some of the plants that we've been working with in our group in Tanzania, and this is Monanthotaxis discolor. This work is done by the three of us, but it was the work of the students who was Dominic. Where do I move forward? Okay, for a long time in University of Dar es Salaam, we've been working with the family Anonese, which has a lot of, which is very, very rich, and then to which the genus Monanthotaxis belongs, and which is about 60 species. And the plant that we worked on is Monanthotaxis discolor, and this is because it is a rare plant, but is endemic in the Eastern Arc Mountains. And we found it in the northern part of Mbeya region, and it was really by accident when our botanists were working there and found this plant. And this plant was then, and the Eastern Arc Mountains, these are part of the two global biodiversity hotspots, which include the Eastern Afro-Montane diversity and the coastal forests of Eastern Africa, which are stretching all the way from Kenya to Tanzania. And there are the two, that is the Afro-Montane and the coastal forests. And the plant that we worked on under the IUCN is categorized as an endangered species, and is found in the places they found there are a lot of activities that is going on, and once we are lucky to find it still there. And so the normal procedures that we take in phytochemistry was the extraction in order to isolate these compounds. And so we were the ones who are working now for the first time. We worked on this plant. And of course, we did the normal extraction and isolation, which is also done with a column chromatography. And then also we did some fractionation with TLC, and then detection by using the UV, and also VLC, and then continue with the work in determining melting points, infrared, and also UVVs, and also establishing using mass specs. And we also did proton and carbon-13 NMR, as usual. Because we had, we were able to do this through collaborations. Botswana was also involved, but also other universities that we are collaborating with. And from there, we were able now to elucidate the structure of some compounds. We also did some brine shift lethality tests to see the cytotoxicity, and also we did antibacterial tests, in which we use E. coli and Streptococcus aureus and the Pseudomonas aeruginosa, and also we did antifungal tests using agar-well diffusion, using Aspergillus niger and Candida albicans. I'll go straight to the results and discussion. And the compound that we want to report here, which is the compound of interest, is the compound number 1, which is 3613 trimethyl 10 oxabicycle 722 dideca 136 triene 5811 trione. We gave it a name, discoronide, by taking the name from the plant where it was found, because it was a new compound to be isolated from the plant. And the IR gave those absorptions, which gave us the presence of an alpha-beta unsaturated as an alpha-beta unsaturated ketone. And the proton NMR gave us 10 signals, but those of most important are those ones which are from proton and COSY that showed us the multiplets which enable us to come up with what is a conjugated system of 11 carbons with a lactone moiety, and that was a compound 1. So that is the lactone moiety, as you can see in from 1, 2, and 11. And this compound, actually, there was an analog that was known in the beginning, and that analog was actually synthesized. And this was for the first time now we had actually was isolated from a plant. And as you can see, you have in the carbon number 12, alpha and B, that was the bit unsaturated ketone, and the unusual member green. So through COSY and HBC, so we have the 6-membered lactone ring, and then we have the allotype group, and then this unusual structure, this is the one that I said that had previously been synthesized, and for the first time now, we reported it from a natural source, was reported from a natural source. I'm talking about then. And these are some of the correlations, important correlations, HMGC correlations of the compound. And the compound is crystalline, white crystalline, very good crystals, and hence we didn't manage to get a crystal structure of it after a lot of struggle. And these are some of the other compounds other than the compound of interest that we are reporting, that we are isolated and identified in that particular plant. And then we went now to look for biological tests. We did a brine shrimp test for the reality, and as you can see, the water extract, we are the most toxic extract with LC50 13.56, and of course methanol, dichloromethane, and the water. And we are suspect because of the presence of those compounds like alomandrin, and they could be responsible for the activity of those extracts. Because then, for the compound, now the compound 1, the compound of interest, it exhibited high toxicity levels. That is about 5.8 LC50. And these are the antimicrobial activities of the crude extracts. As you can see, the dichloromethane, methanol, and petroleum ether of the root and stem buds exhibited high antimicrobial activities. And then we also did antimicrobial activities of the pure compounds, and the pure compounds we are active to Staphylococcus aureus and Pyoruginous, but not in the E. coli. And the new compound showed a wide range of activity in both bacterial and all tested fungi, that is Candida albicans and Aspergillus niger, but had a low inhibition activity compared to the reference drugs in both cases, where we use now ampicillin and fluconazole in this particular case. The minimum inhibition constitution of the active samples, compound 1 and 3 showed a wide range of antimicrobial activities as observed in the screening. Compound 3 was very active against Candida albicans, and compound 3 also was very active against Candida albicans in both Aspergillus niger and Staphylococcus aureus. So by conclusion, you can say that in this work, we managed to isolate secondary metabolites from the Monanthotaxis discolor for the first time. Because we established the structures of the isolated compound, we evaluated the in vitro cytotoxic activity and the microbial activities in both crude extracts and pure compounds, and is an important contribution to the Monanthotaxis discolor, because we are the one to work in this plant for the first time, but there are people who have continued working on it. And we can say that Monanthotaxis discolor is a potential plant for further investigation for antimicrobial constituents. Thank you very much.
Thank you very much for your presentation. Any questions or comments?
Thank you.
Our next presenter will be S4C40, anti-hyperglycemic effect of shea-based imines derivatives. Are you here? Charlotte Gaita? Yes, go on. 10 minutes, 10 minutes. Mr. Gaita, I have the floor now. Thank you. Has a pointer. Wow.
Non, c'est bon, c'est bon. C'est bon. Hello, everybody. My name is Charles. I'm a doctor in the pharmacological laboratory. I have the honor to present our work entitled Anti-Hyperglycemic Effect of CIPS-base imine on glucose tolerance test in heart. To this end, here is the plan. Diabetes is one of the most widespread chronic diseases in the world, affecting millions of people and leading to serious complications if not well controlled. The management of diabetes mainly relies on blood glucose regulation by insulin, oral medication, and lifestyle change. However, despite current treatment, many patients face challenges in maintaining stable blood glucose level and preventing long-term complications, highlighting the need to discover new therapeutic approaches. Many studies had shown that CIPS-base imine have effect anti-inflammatory, antioxidant properties, anti-hyperglycemic potential, notably improvement of insulin sensibility, insulin secretion engine inhibition, especially alpha-glucosidase, dipeptidyl peptidase 4. The objective of this study is to characterize the effect profile on blood glucose of CIPS-base imine in normoglycemic rate and glucose tolerance tests by peros and intraperitoneal route. To achieve this objective, the following material
has been used. The plant material consisting of pharmacological ligands CYP-base imine, NF series and LAD series. The animal material consisting of Wistar-Kyoto rate. The following material enable us to conduct pharmacological tests. In the glucose tolerance test by Peros and intraperitoneal route and normoglycemic rate. Fasting rate was divided into two groups, control and treated. The baseline blood glucose was determined 90 before the administration of physiological water to the control group and gave series, NF series and lied at 30 milligram by kilo Peros and 30 milligram kilo per intraperitoneal and laid 90, 20, 21 at 30, 100 milligram by kilo Peros and laid 100 milligram by kilo intraperitoneal. Glucose administration oral at 4 gram by kilo Peros. The baseline blue glucose was determined at T minus 19, T0, T30 minutes. In the normal glycemic, 5 NF 22 and lead 20, 21. The baseline blue glucose was then measured every hour for 4 hours. The administration of NF 26X29 did not prevent the hyperglycemic peak, while the administration of NF5, NF22 significantly prevented the hyperglycemic peak. In this intraperitoneal glucose test tolerance, the administration of NF5 and NF22 did not prevent the hyperglycemic peak. In normoglycemic, the administration of NF5 and NF22 did not modify the baseline blood glucose level. The administration of LAD series 90, 20, 2021 at 30 milligram by kilo per os did not prevent the hyperglycemic peak, while oral administration of Light 21 at 100 milligram by kilo per os significantly prevented the hyperglycemic peak. In intraperitoneal glucose tolerance test, the administration of lead 21 at 100 milligram by kilo per os significantly prevented the hyperglycemic peak. In intraperitoneal glucose tolerance test, the administration of lead 21 at 100 milligram by kilo significantly prevented the hyperglycemic peak. This result is comparable to the metformin. In normoglycemic, the administration of lead did not modify baseline glucose level. In conclusion, NF5, NF22, and lead 21 are not hypoglycemia. During an oral glucose tolerance test, NF5, NF22, and lead 21 are anti-hyperglycemia. In intraperitoneal glucose test, lead 21 have anti-hyperglycemic effect. NF5 and NF22 would act upstream of intestinal glucose absorption, and lead 21 would have a peripheral tissue action. Thank you.
Thank you very much for your presentation. It's S4, C42 here. Questions, please. Just 2 questions. Or comments. Either come here or use your teacher's voice.
Très bien. OK.
What I'm saying is that diabetes, men do not like diabetes. They are not speaking about this. What are diabetes is speaking about? And what is the problem with the actual medication? What problem he wants to solve? The pruritics are not well set up.
Oui, I can.
Have a discussion with him later too.
Yes.
You understand?
Ouais, si je peux répondre en français.
What type of diabetes
Ouais.
are you talking about?
Oui.
Half type 1, half type 2? And what problem are you trying to solve?
Alors, vous dites que on a mal posé le sujet. Hein? Comment la problématique. OK. Oui, en fait, il y a plusieurs modèles que nous utilisons. Le modèle normoglycémique et le modèle de test de tolérance au glucose. Maintenant, si on voit que les résultats sont concluants avec les deux modèles, c'est en ce moment qu'on va poursuivre le travail en faisant les tests sur le diabète, soit de type 1 ou de type 2. Mais probablement, nous travaillons plus sur le diabète de type 2. Maintenant, ensuite, la perspective ici, peut-être vous aurez dû me poser la question, quelle est la perspective de votre travail que vous venez de présenter? C'est peut-être de tester ces molécules sur le diabète de type 2 ou alors le diabète de type 1. Mais là, nous avons utilisé les deux modèles, le modèle normoglycémique et le modèle sur le test de tolérance au glucose. Je ne sais pas si j'ai bien répondu à votre question. Voilà. Mais sinon, la médication elle est très nombreuse. Ouais. Oui. Donc,
Thank you very much. Please encourage my applause. Is Amadou Ibrahima here? Ibrahima, page 19, physiochemical study of honeys from Southern District of Senegal. If not here, can we take a paper from yesterday, page 16, promoting green chemistry in Africa for more food security and sustainable agriculture. Dogo Sek. 10 minutes. 10 minutes. 10 minutes.
Okay. Ladies and gentlemen, the theme I was supposed to present yesterday is promoting green chemistry in Africa for food security and sustainable agriculture. The challenges of the 21st century is that ensuring food security in the face of population growth, green and low-cost energy, environmental safety with economic and social progress, for which Africa has a great potential. Those potentials are the enormous agricultural potential with available land, rich biodiversity and capacity to contribute on the global scale, and the population growth with a majority of youth. Why promoting green chemistry in Africa? First of all, it aims to reduce or eliminate the use and generation of hazardous substances in chemical processes, and number two, to contribute to sustainability because addressing environmental, economic, and health challenges. Why is it crucial in Africa? Number one is sustainable agriculture is key to ensure food security. Number two, a way to help transforming agricultural practices by introducing eco-friendly and innovative alternatives. And number three, to reduce harmful chemical inputs and their negative impacts in soil, water, and resources. I just want to share some application in the Senegalese context. The first one is the development of natural biocides. The problem is that the intensive use of synthetic pesticides and fertilizers with economic numerous side effects on human, animal, and environmental health. Number two, in terms of alternatives, We have used local plant species to develop natural and ecological insecticides. The benefits of this is that, first of all, lower toxicity for ecosystems. Number two, availability of local material. And number three, cost reduction for farmers. For this, I just want to share the example of developing natural pesticide from Bossia senegalensis, which belong to the Caparidaceae family, largely found in Africa, and mainly in this ecosystem you see here. Very poor soils and drought conditions. For this, I refer to one publication I did in Journal of Chemical Ecology. You can see here, and you can consult. Application number 2 is the analysis of pesticide residue in soil, in water, and also in agricultural products. The problem here is that is a risk on health and environmental related to pesticide residue in soil, water, and agricultural products, which lead to the need of rigorous monitoring of pesticide residue in agricultural products, soil, and water. And the action is to develop an appropriate system for the context to analyze pesticide residue and monitor agricultural treatments. The benefits of that, 3 benefits. First of all, health, consumer protection. Number 2, preservation of natural resources. And number 3, optimization and follow-up of agricultural treatments. Just here an example of to analyze pesticide residue in peanut groundnut, which is a ground very important in Senegal, using a multi-residue method. CATSAIS analysis. CATSAIS is quick, easy, cheap, effective, rugged, and safe for analyzing pesticide residue in groundnut. Application number 3 is the valorization of agricultural residue and wastewater treatments. The problem here is that agricultural residue and wastewater are often underutilized despite being valuable resources. The proposed solution here is to transform agricultural residue into biofertilizer and the use of residue of wastewater treatments in some poor soils. 3 benefits here: improved soil fertility through biofertilizer. Number 2, to valorize the wastewater residues. And number 3, circular agriculture, where wastewater is a resource. Here I just share 3 examples: the use of rice biomass with paddy products and transforming, using straw and using husk, with a content of 80% for straw and 2% of husk. Number 2, using for peanut, that 1 kilo of peanut gives, after shelling, 0.3 kilo of shell after shelling, which we can use as amendment and fertilizer and substrate for vegetable microgardening. Number 3 is to use Tifa, which is a weed largely found in irrigated conditions in the river valley in Senegal, with the benefits you see here. Last application is energy production from indigenous plants and livestock residue. The problem here is that dependence on expensive and polluting fossil fuel in rural areas. The solution is to use the use of invasive plants, local plant and livestock residue to produce green energy, with 3 benefits: energy autonomy for agricultural operations, cost reduction in energy for rural population, and number 3, to valorize local resources while protecting the environment. Just here, using for biogas fertilizer as part of a natural biogas program in Senegal, which began in 2009. Studies have shown that 10 meter cube biodigester produce 52 tons of organic fertilizer per year. Number 2, the organic effluent can be used for forest production and fish farming. And number 3, it is essential that the annual use of 10 meter cube biodigester by a rural household of 10 people represents the use of 50,500 kilos of wood, thus making a significant contribution to forest conservation. Here you see Tifa in the river valley. I want to end with the need of strengthening Africa's capacity in green chemistry. The problem here is that green chemistry is still an emerging sector in Africa and requires significant support in terms of skills and infrastructure. The priority need in this way is modern infrastructure and equipment for research and implementation, the need to train human resources to build competence multidisciplinary teams, and number 3, international collaboration program to share knowledge and technologies. In strengthening capacities building, an example is to solve a problem which is difficult access, pollution, and remote areas of less developed regions, owing to the limited availability of energy, equipment, technology, training personnel, and other key resources. One solution here is using passive sampling devices, which is a technology, very simple technology, analytical tool that sequences and concentrates bioactive organic content from the environment. For this, we are sharing an international collaboration between scientific in Senegal and Oregon State University. We use here in a laboratory which is Ceres Locustox, Regional Research Center in Ecology and Environmental Safety here in Senegal. The technology is here, the center is here. We can give all the contact with this laboratory and with this institute. Yes, to end with the necessary of the collaboration, the need to mobilize funding to develop those programs which are proper. In conclusion, green chemistry, we think, offers concrete solutions for sustainable agriculture and food security in Africa. Now it is time to strengthen Africa's capacity by investing in modern programs and infrastructure, and we call for action to encourage public policies to adopt strategies that promote green chemistry, to stimulate regional and international collaboration, to share innovation and the best practices. Thank you very much. Ready for attention. Thank you very much. As you know, green chemistry is emerging in Africa because it is a way to permit chemistry to contribute to the development of agriculture. Between chemistry and agriculture, it's a very long story. Without chemistry, the green revolution would not be what it has been, but while proposing techniques to protect crops and post-harvest, but also to contribute for fertilizer. Now, because of the necessity in Africa to promote our agriculture, to feed a growing population, we still need fertilizer. We also need to protect our production. So we need new technology to contribute to sustainable development in our continent using fertilizers and pesticides which are less polluting and with less negative effects in animal health, in human health, and in environment. For this, we need infrastructure, equipment, and well-trained personnel to attain this objective. Thank you very much.
Thank you very much, sir, for your presentation. That was lovely. Is Mbaye here? Mbaye? No. I believe that's the last presenter for this session. Thank you very much for your attention.
Ban heure lay durer après. No. Hello, ladies and gentlemen. Good morning. We can take a coffee break and also a poster session. Please, coffee break plus poster session. Kind regards.
No.
ça va pas.
Juste pour voir est-ce qu'il est vraiment, je peux voir les commentaires. Vous êtes du Sénégal?
Oui, oui, je suis d'ici, oui. Je fais la thèse de co-tutelle entre le Sénégal et la France. Je n'ai pas encore commencé à faire la ouais. Là, ça vient, ladies and gentlemen. Là, ici.
My own is next session, so I can send my slides.
Yeah, you don't have in through USB key?
I don't have it.
Yeah, you can send me through email first. You say what? For your presentation?
Yeah.
Okay, you send it by mail.
By mail?
Yeah. Why not for me?
pense que c'est moi le premier qui va commencer. Ok. Je me vérifie dans le dessin,
C'est ce qu'il est en train de me dire, le policier là. On a dit que ça serait éligible, c'est par exemple, les
c'est pour cela que je viens Oui, oui.
Probably in another circle.
l'ordinateur. Voilà, ce sera aussi.
Yeah, no, my D comes out.
Hello. Please, a moment. We are preparing
circle, but I think
the
it's really
coffee break.
interesting the
Now I would
addition of
like
this
to
shaded
have
area.
here all the RSC
Mine is
grantees
the challenge results
so
actions,
that we
but
could
then,
take a picture
adding in
with
enthusiasm.
the RSC
And I guess,
representative.
you never think of, yourself as a
RSC
specific type
grantee,
or
where
the
is
things that
Deborah
are different
Olubumbi?
than more typical Ds.
Where is
captures, I guess, the traditional D would be the challenge results in action focus, but then it says, unlike others with the D style, you dislike environments that are pessimistic or dull. So, anyway, it's really interesting, and I think it does reflect the way that I
all the
operate.
RSC grantees, come here please. You are IUPAC grantee after. Alors, you are IUPAC. IUPAC, it's after when the president of IUPAC comes. Where are the RSC grantee? Alors, we said one from Nigeria. No, Burkina, okay. Mauritania. And the others come from Humphrey Samuel. Samuel Humphrey. What? Wait one moment. Bilkisu, you are IUPAC. Yes, you take. Samuel, where were you? Samuel, Shekha, and who else? You are IUPAC. I wanted to gather all the RSC grantees. Alors, 1, 2.
I know that the from Nigeria, Ike coming.
Okay. Baax na waaw. Ak David, okay. Radisson Blue. Hotel Radisson, waaw. Baax na waaw. Merci, jërëjëf. Baax na waaw. Loolu la ma baax. Ok, jërëjëf. Alors, David, Ike. Deborah Olubumbi, Aderic B.
لا هذه حاجة مرجع. خذ من غادي غير كل هذا عندك كبير ما تدخلش
لازم كبيرة.
لا دابا انت من غادي تجي تخدمي ما تقدرش تخدمي بهذا وبهذا حيت هذا غير باش كتشارجي باش كتغيري صافي حيت انا ما غاديش يدخل هذا حيت هذا شويه عريض ماشي بغا نقول انا حيدته باش
سينا حتى عندك ماشي مشكل.
حتى حدا عندك
S'il vous plaît, on va commencer la session, s'il vous plaît.
يرفق عنا يرفق عقله ولا يرفق عنا انت باش تشوف شي صافي انت عنده صافي انت صافي خليها هنا باش تكملي في الاورديناتور ديالك باش من بعد نخليها غير تحت فهمتي نخليها هنا
Alors, en tant que président, je vais me mettre où?
Normalement, il y a un banc, mais vous pouvez parler après prendre une place là-bas, mais des fois...
Un micro, quoi.
Sinon, vous voulez à côté de ici.
Ouais, d'accord. Alors, prof, oui, Aziz, qu'est-ce que vous voulez qu'on dise de vous?
Est-ce que vous écoutez pas ici? Est-ce que le micro fonctionne?
Non, non, il ne fonctionne pas. Le off ne marche pas.
C'est tout, il n'y a pas beaucoup de choses. Essayez de le dire comme ça, pour mieux comprendre, pour trouver les résumés de toute façon. Moi, je peux le dire comme ça. C'est bon? Attendez que je vérifie ce que c'est. Voilà, c'est ça. Je vérifie. Pour moi, c'est bon.
Please.
Anderson, Mungu dengan mawar ya. Sampai konferensi ya, wai. Nene telepon ke fai. Kalau dengan ada kita dimak. Okay. On va commencer.
S'il vous plaît, est-ce qu'on peut commencer, s'il vous plaît? Ceux qui sont derrière, prenez place, s'il vous plaît. Alors, hello everybody. I present the Professor Aziz, excuse me, parce que c'est... oui. I present the Professor Aziz Amin. It's a professor who present here one plenar conference. The title is Recent Advances in the Development and Application of Nanozymes and Novel Chemical Catalysis. The Professor Amin Aziz is currently a full professor at Hassan II University of Casablanca in Morocco. He obtained his PhD degrees from the three University of Bruxelles in 1993. For the past oh là là. Alors, c'est parti. Alors, he has authority of 200 paper, several in coordinator of journal Biosensor and Bioelectronic, and of November 224, his research indicator on Google Scholarly include H-indexed of 16.2 and 12,700 citation. He is ranking among the scientists all world in 2020 and 2020 and 2020 2021 and 2022 and 2023. Now I just report here the recent advance in development and application of nano-ZIM as novel chemical catalysis. Professor Aziz Amin, s'il vous plaît.
Yeah, merci, Monsieur le Président. Thank you, Chairman. I will try first to give you an overview about what is NanoZyme. And let me first thank the organizing committee for inviting me and to share the result of our laboratory and also to learn from the experiment presented here in this conference. Today, I will talk about NanoZyme, which is something new, a few years ago, and is nano-catalyzed, if you want, but will mimic enzyme. It's like artificial enzyme. So this is something new. We will be interested in that. I try to follow this plan as I can. If you look on the Scopus and you see the paper published about NanoZyme, you see it starting a few years ago, maybe 5 years ago, and now this year is almost 2,000, more than 2,000, only for this year. I presented this conference last year, it was about 100 papers. You have an idea about how many papers published on NanoZyme per year. It's more than 2,000. So what is the definition of NanoZyme? You have here definition, which is not, it's still controversial, let's say. Is nanomaterial. Nanomaterial is less than 100 nanometer. And catalyze the conversion of substrate to product, follow enzymatic reaction, but mechanism maybe can be different. So it's a nanomaterial, size less than 100 nanometer, make catalysis of enzymatic reaction, the same substrate, the same product, maybe follow Michaelis-Menten kinetic, but not mandatory the same mechanism. This is usually the definition, accepted definition, let's say. To have an idea about history about artificial enzyme, NanoZyme is a part of artificial enzyme. The first time that the name artificial enzyme was coined, was used for the first time, is in 1970. Then NanoZyme, 2004. And after that, you have many enzyme nanomaterial that mimic enzyme activity based on nanoseria or magnetic nanoparticle too, have peroxidase activity, and you can find many other based on vanadium, based on, let's see, on molybdenum, and so on. And you have many applications, included last one, where we can combine, in our lab, we combine molecular impregnating polymer and nanocells. Just 2 slides to remind you about enzyme, natural enzyme. Natural enzyme follow, most of the enzyme follow Michaelis-Menten kinetic, and you have 2 constants. Michaelis constant, which is the Km, which is, let's see, doesn't see you, anyway. This is the Michaelis constant, which is equivalent to concentration, which corresponds to the half of maximum velocity. Then you have another value, another parameter, which is maximum velocity. It's not constant. In fact, it depends on concentration of enzyme. But we are interested in catalytic constant, which is maximum velocity divided by concentration of enzyme. And these give you an idea about the turnover, how many substrates manipulated by the enzyme per unit of time. So the enzyme have two constants. Constant Michaelis-Menten give you an affinity of the enzyme for the substrate, and the second give you the turnover. Here you have all the kind. If you make classification of the enzyme, you have all the kind. A few years ago, there is only 6. Now we talk also about 7 kinds. You have oxidoreductase, transferase, hydrolase, lyase, isomerase, ligase, and translocase. This is the most enzyme. Any enzyme should be one in the one of these kinds. So this is classification of enzymes. How about nanozyme? Classification of nanozyme. If we are interested in a compound of the nanozyme, we have this classification. You have, for example, is carbon or other metal, for example, or it's not clear, or metal organic form, and so on. If it's metal or oxide metal or carbon, and so on.
Well, it's an observation about this group because there are a number of heads of NCAs and CDTs at this table, which I notice it's probably the largest confluence of them. And so it's interesting because your jobs are in between. You have to use your influence. You don't necessarily have the authority in all cases because
the other classification, we can see about a family of enzymes. You have catalase, oxidase, peroxidase, glucosidase, protease, phosphatase, and superoxide dismutase, lacase, and so on. So some nanomaterials that have lacase activity. Lacase activity is like polyphenol oxidase or phenol oxidase. We make oxidation of some phenol. Peroxidase is substrate plus hydrogen peroxide. You can have some metal, nanomaterial, that have the same activity, the same reaction like peroxidase. So all that nanomaterial can mimic this enzyme. So we can make classification according to which enzyme or which compound of the enzyme. The synthesis of this enzyme, how we can do that? Sorry. We can, as you do for preparation of nanomaterial, you can use, for example, co-precipitation, hydrothermal, solvothermal, and so on, or even electrodeposition or other things. Exactly, we can have the same thing. But the most used here is electrodeposition, co-precipitation, and solvothermal, the most used for nanoenzyme preparation. I'll give you some example. Lacase mimicking nanozyme. Lacase is enzyme that work with the phenol. But if we look in this enzyme, we found that you have metal. This is copper metal, and have two amino acids. One is cysteine, one is histidine. So if we would like to develop a nanomaterial mimicking this enzyme, we can also use copper, as you see here, copper plus 2 amino acids or similar, and then in this condition you find a precipitate which have activity mimicking the activity of enzyme, bio-inspired if you want. So this is like artificial. We call that nanozyme because it's nanomaterial. So we apply that, as you see here, this is a natural enzyme, and this is artificial or nanozyme. You have copper, you have C for cysteine, H for histidine. So this is artificial. Both of them give coloration, give the product, which is colored. And even if you see the two constants, as I see, Km and Vmax, is almost the same. For example, here, for both of artificial and natural enzymes, almost similar, and the same for velocity. I should say that turnover can sometimes, for nanozyme, is even better than enzyme, but not selectivity. Selectivity, enzyme still superior. Again, lacase can be used not only for detection of phenol, can be used also for degradation of phenol. And you can use it for many phenol that can be eliminated thanks to this using nanozymes. Another example of decontamination is using organophosphorus hydrolase. This is enzyme can eliminate organophosphate, which has pesticide. But you can mimic this enzyme and using nanomaterial, which is in structure similar to the enzyme, only in active site. I mean, not all the enzyme. Enzyme has a high molecular weight, but you use only the active site. And you get the same results. And you can hydrolyze methyl parathion, which is very, very highly toxic, and you mimic this natural enzyme, which is organophosphorus hydrolase. Another example is CO2 capture, and you know that's very, very important if we would like to decrease the CO2 in the environment. So you have in this journal, they published that in the cover of the special issue. This is the artificial enzyme, how we mimic this enzyme. We can just see which metal, which amino acid, and try to do something similar. So we select, we see the metal, and then we do the same. The metal that you have here is the zinc. Some amino acids near to the zinc, like histidine, and we can use histidine or imidazole because this structure is a little bit similar. And at the end, they succeed to fix CO2. So this is something interesting. We use 2D graphene doped with nitrogen and zinc in order to have something mimicking this enzyme, which is anhydrase carbonic. Anhydrase carbonic is enzyme naturally fixes CO2 at high turnover, but we would like to mimic this enzyme in order to decrease or to reduce the CO2 in air. So we use that. In fact, this capture of CO2, and we can determine its activity with artificial substrate and give color to it. Advantage of using nanozyme is stability, because it's not biological material. As you see here, highly stable even at high temperature. This is the red one, which is artificial. However, natural enzyme decrease because it will be denatured. The same if for the pH has a wide pH range. However, for natural enzyme, it's different. It's only working, maybe it's alkaline pH in this case. Another example, hydrogen production. There is natural enzyme, hydrogenase, that can produce hydrogen, natural. They can make conversion of proton to hydrogen using NADH to NAD. This is natural enzyme. But if you study this natural enzyme, in nature we have three that using as a metal iron or nickel or iron nickel to do. But we can use it artificial and use it nickel and cobalt, and instead of NADH we use aluminium. In this case, the author, not our lab, the author succeeds to produce hydrogen at this level. This is just to show you how interesting artificial enzyme, working as chemist for something biological, which is very, very important. Many years ago, 20 years ago, we developed our lab in collaboration with others in Europe, artificial peroxidase. But at this time, name nanozyme doesn't exist. And also when we developed that in 2003, is artificial. It works exactly as peroxidase because when you added hydrogen peroxide, as you see in the reduction, there is a high amplification of signal. This is only due to hydrogen peroxide. Then many years ago, after we repeat this synthesis in order to have nano material and use it as a nanozyme. In fact, Prussian blue can be used either on the electrode or in solution. You can use it in the electrode and for many applications, and you can use it also for colorimetric determination. And use it as artificial peroxidase. This is some application. We can use it, for example, for lactate. People who do sport, increase concentration of lactate. We can follow concentration online of that if you have electrode that you can put it on the screen, on the skin of the body. You can do that provided that you have flexible electrode. Flexible electrode based on polyimide or something like that. This is we developed also in lab, and we modify the design of the electrode using laser, CO2 laser or something like that. And we can do even at 180 degrees, and we make electrochemistry, and it's still working exactly as you use it normal. Because when you put it on the skin, it should be flexible. You can twist without problem. Sorry. So after that, there is many peroxidase, artificial peroxidase if you want. Peroxidase is the most studied. Most studied, let's say, artificial enzyme is peroxidase, and either electrochemistry or spectrophotometry. And spectrophotometry, you have family or many other substrates which give colored products. Here you have many products. The most used is TMB. TMB gives blue colored. This is the most used. But as I see, nanozyme doesn't have the same mechanism as enzyme. Here is an example. If you look on peroxidase, natural enzyme, the enzyme reacts with hydrogen peroxide, give an intermediate, we call that compound 1, then the same intermediate reacts with the substrate, for example, phenol or other thing, and give a second substrate, which again came back to his initial state. This is, it means that enzyme react with hydrogen peroxide and second substrate. However, for artificial enzyme is something different. Is like Fenton reaction. For people now, Fenton reaction, it means that just react with hydrogen peroxide, and you have as product hydroxide.
Logic, we're systems oriented, we're reliable,
it means
we provide in-depth analysis.
Enzyme react with hydrogen peroxide. There's interference, I can't do.
Yeah.
So,
but it's coming from our data-driven experience, and we also
so it means that
I think those were the main ones in contribution.
React with hydrogen peroxide, liberate hydroxyl, which react with second substrate, but enzyme doesn't react with the second substrate, or artificial enzyme doesn't react with the second substrate. React only with the first one, and give hydroxyl, who go and react with the second substrate. That's why, if you prepare magnetic particles that have peroxidase activity, the iron tree, which is formed on the surface of this nanoparticle, is not regenerated because it's like Fenton reaction, and you lost it. And from the inside the nanoparticle and outside the nanoparticle, little by little, you consume all the iron that you have. At the end, when it's totally consumed, it's not anymore, it doesn't catalyze anymore the reaction. That's why even the structure change. If O2 O3 and if O3 O4. So this is not a real catalyst in this way. What some author propose, in order to increase, let's see, the activity or turn over the enzyme, is to use magnetic nanoparticle and to cover with imprinting molecule, is polymer with some cavities that has affinity for TMB, which is substrate. It means that you accumulate substrate and then you add hydrogen peroxide. In this way, we can increase the affinity and the turnover also. Just in one or two slides to show you what is molecular imprinting polymer. Is a polymer you developed with all, let's see, monomer, crosslinker, initiator, everything, and you have a polymer, including templates, including analyte. Then you remove your analyte, and you have behind some cavities which correspond to the top layer analyte in shape, in size, and in a way that you can use it to have affinity for your template. So at the end, you have something like that. This is what I mean here. This is cavity. All that is molecular impurity in polymer, and this is cavity that has high affinity for substrate. So now we move to some application about nanozyme in biosciences. The most used application is immunosensing. Why that? Because a nanozyme has nanomaterial, can have, let's say, high affinity and high turnover, but not specificity as enzyme, natural enzyme. In the case of immunosensors, what happened? That this is antigen analyte that we would like to determine. It is recognized by the antibody. So the selectivity is due to the antibody, not to the enzyme. The enzyme used here is only for the amplification of the signal. Usually, this is immunoassay. And the substrate you added at the end, after washing, eliminating sample, everything, you added your substrate. So there is no problem about interference. That's why, in this case, it's better to use, instead of enzyme, use, let's see, nanozyme. Use it only for turnover. And most of immunoassay now are developed using nanozyme instead of natural enzyme. This is an example. We use nanozyme based on palladium and iridium for prostate-specific antigen determination. As you see here, this is natural enzyme and this is artificial. And you see wide range, as you see from the color, respect natural enzyme. You can use it also for lateral flow, for a rapid test. You can use it. And you have here a table for many applications. And even this is only a part. There is many others. This is only taken in 2020 if you want. Some work developed in our lab by two PhD students that develop immunoassay with peroxidase, Prussian blue, since we have wide experience with Prussian blue. We modified our antibody with Prussian blue, and we use it for application for milk species adulteration. What does it mean, milk species adulteration? You know, you can have milk from a cow and milk from goat, but milk from goat is more expensive than milk from a cow, and some farmer tends to make adulteration, take some milk from cow and add it to the milk from goat in order to make money. But we can, if he would like to do that, at least he make 10%, 50%, something like that. We developed method, immunoenzymatic method, that can detect even 0.1%. So he can never make money with that. So for that, we have antibody that detects immunoglobulin, because immunoglobulin is specific for cow, for goat, and so on. And instead of using enzyme, we use Prussian blue, as you see here, modified with antibody, and we have a coloration at the end. Peroxidase can use TMB as a substrate, and the product can be detected either spectrophotometrically or even with smartphone or electrochemically, because it's also electroactive. And as you see here, we make a calibration. This is the control with only goat milk. If you add 0.01% of cow milk, we can detect it. It's look the bar error here and bar error, and there is big difference. Even 0.0. This means 0.1 milliliter of cow milk in almost 1 liter of goat. We can detect it. Another application related to the DNA sensor. DNA sensor, it means you have one probe, which is one strand sequence of DNA that has affinity for the complementary, for the target that you would like to detect. These complementary give you the specificity of the analysis. But how we detect that? We added gold nanoparticle. Gold nanoparticle has peroxidase activity. and can't link with the DNA because it's negatively charged. We modify gold nanoparticle with cysteamine. It became charged positively, then it is attracted by the DNA, and then we test its activity, peroxidase activity by adding substrate, and we detect color. So it's easy. It's a paper sensor modified, and we can detect the complementary DNA or RNA or OGM or many other applications. This is only the process. Well, this is application optimization and so on. I go fast in order to show you other examples. This is another example with magnetic nanoparticle modified with a probe sequence, which is in blue, and you would like to detect the read sequence. Read sequence is corresponding to something, can be microRNA for disease, or can be other sequence let's see, in a sample. How we detect that? We make competition with another sequence modified with nanozyme. And after that, we make the activity, and we detected that. As you see here, the activity decrease, and you have two calibration, one with natural peroxidase and one with artificial peroxidase. And almost the same linear range, both are parallel, is almost the same sensitivity. Can be used. This work just published by Royal Society of Chemistry. This is the chemistry if you want, but since we are chemists, this is first how you modify with magnetic nanoparticle. Of course, we use carbodiimide, most used, the golden standard. Yes, for modification, if you have amine and you have carboxylic acid. And after that, you prepare your nanoparticle. You modified also with citrate in order to have some carboxylic, and also you modified with carbodiimide in order to immobilize some protein or something like that, and can be used for the application. Another example, not from our lab, it's something easy as idea, is use aptamer. What is aptamer? It's a sequence of nucleic acid. Now you can find many in literature for any molecule, for any contaminant, you can find some aptamer that has affinity for this molecule. For example, if you use gold nanoparticle, they has peroxidase activity, and you have a color here. You can detect it also electrochemically. This is the response, gold nanoparticle. If you added aptamer, aptamer has affinity to the gold nanoparticle, and thus the reaction doesn't happen. And that's why you have no response at all, because when aptamer is linked, bound to the gold nanoparticle, substrate can't, let's say, there is no conversion of substrate to the product. However, in presence of bacteria, since aptamer has also affinity for bacteria, will react with bacteria and not with gold nanoparticle. That's why you have response here. Gold nanoparticle plus aptamer plus bacteria. So it depends on the concentration of bacteria, signal will be in these two between here. So this is a method that can determine bacteria or any other analyte, provided it has affinity for aptamer. Now let's go to something other. We just published it this year in Biosensor and Bioelectronic. We are asking ourselves, what is nanozyme? Most of nanozyme used are metal, and is something like active site of enzyme. Enzyme is a big molecule, almost 200,000 Dalton, and active site is only 2-3 amino acids with some metal. The most enzyme is something like that. So nanozyme is like coenzyme, if you want. Because, look, this is enzyme, and you have coenzyme or cofactor, who is responsible of oxidoreduction of the reaction. And all this part, we call that apoenzyme. This is very important for specificity, that recognize the substrate. So, inspired from that, we try to do something similar. We use nanozyme as coenzyme, and we use molecular imprinting polymer as apoenzyme, These help for substrate specificity, and these help for catalytic reactions. And this is the first time we developed that. In fact, this year it was published, and we received many comments from LinkedIn about this inspired artificial. And now in our lab, we continue in this way. So first, we prefer to work with magnetic nanoparticle, although it doesn't have high activity as peroxidase, because it's simple to make separation with magnet. But we modified in order to increase its activity. We use magnetic nanoparticle, we modified with lysine and with a copper. And then we, copper after reduction with borohydryl sodium, they become nanoparticle, and these help also for peroxidase activity. Then we cover this magnetic nanoparticle with molecular imprinting polymer. And as you see, Km decrease and maximum velocity also change. So improved catalytic activity. This is a magnetic nanoparticle. We modified with lysine and copper, and then with molecular imprinting polymer. Why we use molecular imprinting polymer? Peroxidase react hydrogen peroxide plus several molecules like phenol. We are interested in dopamine. We use molecular imprinting polymer for dopamine. We are interested in L-dopa. We use molecular imprinting polymer for L-dopa. We just change the molecule because the reaction is the same. And the most of enzymatic reaction is like that. Look, for example, amino acid oxidase have the same coenzyme, flavin adenine dinucleotide, but one specific for L-amino acid and the other for D-amino acid. Even the same enzyme, almost same enzyme, but coenzyme is similar. So here we do the same. We do the same enzyme, but molecular imprinting polymer change. And as you see, for example, in this case, we are interested in DOPA, so the high activity for dopamine. When we change that for example, not for DOPA, for dopamine, we will get one high affinity for dopamine and so on. So molecular imprinting polymer improve specificity, which lacks for nanozymes. Another work we are working now, not published, and this is in collaboration with the university in north of Iraq. They prepare for us nanozyme based on a MOF, and this case has oxidase activity. We use it, taking advantage of our experience in molecular imprinting polymer. We cover it with the molecular imprinting polymer, and we use indirect method for determination of substrate. It means that when you have polymer with some cavity and you added substrate, TMP can go through this cavity and react with nanoenzyme, and you have color development. If in presence of substrate will be in all this cavity, and reaction doesn't happen, you will not see the color. So we have indirect method to determine for any analyte, provided that you have polymer dedicated for this analyte. This work is submitted, let's see. Another work is, let's see, most important for me, is synthesis of nanozyme. Synthesis of nanozyme, as I see, can be co-precipitation, can be many things. But nobody uses laser scribed graphene. We have experience about laser scribed graphene because this electrode from polyimide, we make electrode from that. So we are asking ourselves, why we not make synthesis of this catalyst in one shot? The same time make a synthesis of electrode and also of nanozyme. This is what we did. We added, on the electrode, we added a few microliter of precursors of this catalyst, and at the end we got magnetic nanoparticle, we got activity of peroxidase, oxidase, catalase, and so on. And we tested. This work is, we're still working on that. It's unpublished, so I ask you to not take picture even that. So, at the end, we should make comparison. If we talk about comparison between nanozyme and enzyme, On the left is nanozyme, on the right we have enzyme. On the left, nanozyme is nanomaterials. Low cost, long-term storage, it's stable, it's chemical, yeah. And robust for harsh environment, for pH, acid, alkaline, and so on. However, enzymes have other advantage, high substrate specificity. We can never reach the specificity of the enzyme. This should be well understood. And design can be changed using engineering and so on. Disadvantage of nanomaterial is limited substrate selectivity. That's why we propose to use molecular imprinting polymer. For the enzyme, high cost, limited stability due to denaturation and so on. This comparison, I hope to give you an idea about that, but before finishing, I would like to talk about one slide about other type of enzyme, which is allosteric enzyme. It's a polymeric. And this is an enzyme that controls all the metabolic pathway. For example, you would like to increase this citidine triphosphate. These enzymes, the aspartate transcarbamylase that you have here, have not only catalytic activity, but has also regulatory unit that can change from active to inactive. This is known for the enzyme that control pathway. When we talk about nanozyme, it's not about that. This is something very high, very superior, maybe after several years. Other thing, 2 years ago, it was published an article very interesting that will change the nature after about plastic in the environment. This is by Texas University. They succeed to use some bacteria. Bacteria is only bag with enzyme inside, just to explain. And to use some bacteria, and these bacteria with some let's see, some selection of this bacteria using also machine learning, and they succeed to have some bacteria that can degrade the polyethylene phthalate, which is a polymer, which is plastic, which requires centuries of years to be degraded in the environment. They succeed to have degradation of that in only a few hours, less than 24 hours. And they find enzyme that called POTase. From this paper, after, this is less than 2 years, we found other work about enzyme, how we can immobilize, how we eliminate microplastic, and so on, which is emergent pollutant now. I'm asking myself, can we use nanozyme? Because if we know polyethylene, POTase, and we see exactly active site, we can also develop nanozyme, and we develop which is chemical, and you can use it easily to eliminate the most of plastic. Maybe in a few years we can talk about that. I invite you to attend, to participate. This is the activity of our lab. Every 2 years.
Hey, Jason.
Not me. Every 2 years,
Hey, Jason, one quick question for you. For your 1 day of coaching experience, I want to know who took the picture, 2 of them, and did they enjoy watching you sweat?
Well, sorry. Every 2 years, we organize international workshop on biosensors since 2003. It's more than 20 years. The last one was in Marrakesh. More than 20 countries participate. Almost 90, 100 persons attend this conference. Most of experts in the world participate. As myself, editor of Biosensor Bioelectronic, we know each other, so we came to Marrakesh and participate every 2 years. Other work that we started many years ago, in 2006, 8, 10, then we stopped a few years, and then we resumed again in 17, 18, 19, 22 for the COVID period, and 3, 4, and this year we also organized. And the next one will be in April. And I'm happy to see that some colleague, Abdullah, is here somewhere, I don't know. Yes, he attended also this conference, and I invite you to participate next. So thank you, I'm happy to answer to all your questions. Thank you.
Thank you, Professor Aziz Amin, for this conference for nano zyme and enzyme. Here you have two technology for the synthesis of nano enzyme and the enzyme for natural enzyme. Now I open the yes. Micro. D'accord. Oui.
I think one time. So it's complicated and we have to use it one time. It's not true or it's true? No? Just a comment about MIPS, please. Thank you.
Well, before presenting this conference, I'm not sure if I present nanozyme or MIP, or molecular imprinting polymer. In our lab, we have wide experience with molecular imprinting polymer. And we published recently one paper that fixed problem about non-specific absorption. It was published also in Biosensor Bioelectronics. And we have many other work currently in our lab regarding MIP. I can see we can use it many times, not only one time. The problem how to regenerate that is only with buffer, is with some solution or something like that. We talk about all that. We can use it even paper sensor. We have a MIP, just add in some solution and you can reuse it again. And we show that in some diagram, how many times reuse it, and the activity decrease about 10%, maybe after 10 cycles or something like that. We have many paper like that. Just follow me in paper or something published and you can see that.
Thank you from
Abdullah.
Yes, Rami Abdullah.
I would like to, firstly, I would like to thank Professor Aziz Amin, which scientists around the continent of the African continent. My question is about, I'm working about the polymers. I would like to ask you the difference between polymers and nanozymes. If I understand, nanozymes are implemented by bio-inspiration. It is a way to implement nanozymes. We have this way also in polymers, which we can implement by mimicry or by inspiration. What difference have you between nanozymes? What advantages can we have in nanozymes, which I think are more resistant than polymers, related to their possibility to have several activities, as well as for nanozymes and for the polymers. The difference between them, I would like to understand. So, I would like listening to you in this new topic, which are very relevant for us here. It is the first time that I'm listening, talking about nanozymes. Thank you.
Okay. I try to give an idea about that, but we maybe can talk even more about that. I have sometimes conference about biomimetic sensor, when we have nanozyme mimicking enzyme and MIP mimicking antibody, because MIP is like synthetic antibody. And MIP has high selectivity, but not reaction, not chemical reaction, not activity. Nanozyme has high activity, high turnover, but not selectivity. The best way is to combine both of them. This is what we did, and it was highly accepted by the scientific community, as I see from LinkedIn and so on. Polymer, we can do mini polymer to model that, to build that according to your substrate in order to have high affinity for your substrate. We succeed to that. But no detection, how you detect that? Enzyme can do that. Nanozyme can do that. Nanozyme can give you electrochemical detection, spectrophotometric, fluorometric, luminescence. We give also for luminescence, hemoglobin, luminescence detection, and so on. But combining both of them, it will be very nice. We can talk after about polymer and so on.
Last question. Last time.
We can talk after. No. Yeah, I see, but I don't have idea about nanozyme using for packaging and nanozyme. What I see is the last time I present something similar and somebody from the food industry asking me how we can use that for food industry or food or something like that. Maybe we can see. Toxicity of nanozyme, it's still a problem because something new and this is also some the disadvantage. And you can use it for industry and for conversion all as I see. For packaging, let me see what now I'm involved in European projects. When I have my work package is to develop a sensing method for production of toxin or something like that. And I should do nanozyme and MIP in some paper included in packaging, and I follow if there is some gas produced or if there is some toxin and so on. So can be used for that. Now, if it's toxic, non-toxic, this is another story. Maybe this is agency that can follow that and see which nanomaterial, toxicity of this nanomaterial and so on. We are a laboratory, we develop a thing, and other do toxicity and so on. But we can use it to follow packaging, traceability and so on, tracking this.
Okay.
Yeah, this one, yeah.
My question was dealing with mainly use Fe2O3 or
Yeah.
Have you tried other particles, other inorganic particles?
Yes, of course. Let me see. Magnetic nanoparticle, then we can use copper, then silver in this way. The most used. Magnetic nanoparticle, copper, silver, molybdenum, cerium, vanadium. This is in this way. Magnetic nanoparticle have other advantage. As analytical chemists, we use it easily to make separation because just make external magnet and you make separation. That can be done with copper and other things. Even if it's not highly active, we modified with copper, we modified something to increase the activity, and we keep magnetic nanoparticle for this property of easy separation.
Okay, ovation, Professor Aziz.
خلى الأستاذ باش دير
You can take your computer. You finish? Here.
Ça passe comme ça
صافي اطلع هو هذاك 30
C'est bon C'est bon
وين تحرك حركه من عندك
ما كاينش معنا
لا من هنا شوف انا واش تحرك
تحرك سي بون
لا انا ما تحركش هذا
لا تحرك
صافي ملي غيعطيك هضر غيبان لك
think to have, yeah, it's okay. It's okay. Yeah, thank you.
Okay, we can start the next session. It's on electrochemistry and nanotechnology. For those who don't know chemistry and health, that's downstairs. Yes, everybody staying for this one. Okay, so we've got about 7 speakers today, about 10 minutes per time. We'll try and keep it to as much as we can. And our first speaker is Professor Mama Razi, and I'll let her
Yeah.
take over.
Thank you very much, Neil. Thank you very much. So I think that it's good transition between what Professor Aziz Amin said and my presentation, because I have learned today that I'm working on nanozyme without knowing that. So thank you very much, Professor Aziz Amin. I will talk about catalysts based on conducting polymers and metal oxide and some application of this kind of materials. So first of all, let me introduce myself. So I'm Mamal Ghazi from Laboratoire Matériaux, Membranes et Environnement from Morocco, University Hassan II Sudan. So we are 3 teams in our group, and we are working on electrochemical sensors for detection of heavy metals and emerging pollutants such as bisphenol based on nanostructure of carbon polymers and bismuth film. And we are working also on fuel cell and about oxidation of ethanol and on conducting polymers and metallic nanoparticles. And another team are working on elaboration, and Professor Zay Amin talked about that yesterday, about elaboration and characterization of inorganic membrane based on clay and phosphate for water purification. So let's talk about electrochemical sensors. So what are we doing? Simply, we are electrochemists, and we are working on electrochemical methods, and we are modifying the surface of the electrode by perhaps nanozyme, I don't know, but we are working on conducting polymers and metallic nanoparticles in the aim of detection of many heavy metals and pollutants such as lead, cadmium, zinc, copper, or pesticide, or bisphenol, what we call emerging pollutants. And also we are working on detection of nitrate and nitrates. And for this, we are using electrochemical methods such as differential pulse voltammetry, cyclic voltammetry, and square wave anodic stripping voltammetry. And our modified electrode, we can work on it for detection, and we can also work on it as fuel cell for oxidation of alcohol. And 2 years ago, we started another topic, which is splitting water. So our catalyst also can be used for hydrogen production. So what kind of material are we using to prepare our nanocomposite or hybrid composites? So we have here, I don't know if I have pointer. So we have our electrode, and on the electrode we can combine different materials, and we can work on metallic nanoparticles such as gold, copper, silver, palladium, platinum. We can work also on conducting polymers, and we have lots of conducting polymers. We have polyaniline, we have polypyrrole, we have also diaminonaphthalene, we have phenylenediamine also. And we have also carbon nanomaterials. We have also carbon nanotubes and graphene. And we can combine these materials to have nanocomposites depending on what we want to do. We want to do electrochemical detection of nitrate. We have to use only conducting polymer. We have to do splitting water. We have to do combined conducting polymer with copper nanoparticle to have more surface area. So this is the preparation of our electrode surface. We can, by drop casting, just put our graphene or carbon nanofiber. Still after, we will carry out conducted polymerization of our conducting polymers, and we can also combine this with nanoparticles, metallic nanoparticles. So electrochemical methods help us to do this very easily. So we can modify our electrode using different methods. So we have cyclic voltammetry, potentiostatic mode, and also galvanostatic mode. So I will explain this just after. Why we are using electrochemical methods? Because electrochemical methods offer several advantages, such as the control of the potential and also the density of the currents. So we can control the thickness of the film. We can also control different experimental parameters, and we will have different morphology depending on what we want. And also for the deposition of metallic nanoparticles, we can use, of course, anodic polarization, so fixed potential, or we can use also galvanostatic mode. I will explain what I prepared this slide. We will see just after why we give great importance to mode of polymerization or the mode of deposition of metals. So I will give some example about our work. So the first example is about electrochemical sensing of nitrate ion using modified electrode with diaminonaphthalene and multi-walled carbon nanotube, and its work of Wissal Salhi. Why we choose nitrate? Simply because nitrate is used as food preservative and food coloring under the form of sodium nitrate. And an excess of this element in the body leads to different diseases such as cancer. And we have, of course, the maximum concentration admissible in drinking waters. So what we have developed is polymer with carbon nanotube, and we've done the polymerization using cyclic voltammetry, and we characterize our film with different methods, cyclic voltammetry, impedance technique, and also SEM. And here is just to show you that the polymerization on bar electrode and also on modified electrode with multi-walled carbon nanotube, and we have an increase in current due to increase of conductivity of the surface. Yes. And here is the scene image of the surface, and we can measure the value of the thickness of the film. And we have only 20 nanometers of the film, and when our sensor is prepared, we look in the response of nitrate solution on different electrode, and we have here the response of nitrate on different electrode, and we can see that the current is multiplied by, I think, 10 times when we use the modified electrode with polymers. Of course, we have studied the linearity range, the limit of detection, and the response time of our electrode. And the second example is about bisphenol. And bisphenol, as you know, is widely recognized as a non-endocrine disruptor and can introduce serious risks to human health, such as sexual anomaly and cancer. And for this, we used this composite with carbon black nanoparticles, it's phosphate, magnesium, and cobalt with phosphate nanoparticles. And we have really very good sensors with very good linearity and very low limit of detection, and we can use also smartphone to collect the measurements. And also I seen yesterday the talk of Shayma. I thought myself that I'm working on green chemistry without knowing that, because why this? In a recent publication about time economy in total synthesis, some of scientists in organic chemistry are working on what we call domino reaction. So electrochemical cascade reaction was also called reaction. Domino reaction is something we can reduce the time of the reaction. If we have 3 or 4 steps, we can reduce the time of reaction to 1 step, and it's called domino reaction. So, to reduce the time of reaction, we minimize chemical products, we produce the polymer or catalyst as needed, we save time, and saving time is saving money, and also we produce the catalyst in very few minutes. And the first example I will give you is about the detection of lead and cadmium. And for designing our sensors, we put together the polymer and also bismuth film. And the sensor was prepared in 1 minute and a half, in 90 seconds. And we have had very good results. Here is the mode of preparation, and we have had very good results with very low detection, respectively for both cadmium and lead without interference. So, the conclusion of part 1 is that the reported approach allows us to develop the composite in only few minutes with a high economy of effort and reagents. And the developed sensor showed very good analytical performance toward lead, cadmium, nitrate, nitrate, also with very low detection limit, and with good repeatability and reproducibility. And it holds gross promise for its wide application in class determination of emerging pollutants such as pesticides also and bisphenol. So the second part of the work is how we can use this kind of material in other applications, such as oxidation of alcohol or water splitting. So we will use this because we know that nanomaterials or nanozyme, I don't know, or nanocomposites have very good electrical conductivity, have very high surface area, and they have unique structures and other properties, so we can use them in energy, indirect alcohol fuel cell. And this work was done by my PhD students, Halim Al-Mahdi, Sana Shimshuk, and also Anas Al-Attar. So it's the electrosynthesis of new catalysts based on polymers and copper or nickel for highly efficient alcohol oxidation. So let's see here schematic cell of electrochemical cells. So in the anode, we have the oxidation of alcohol to CO2, and the cathode, we have oxidation of oxygen. So the main problem in fuel cell, what is it? The main problem in fuel cell is the cost of the electrode, because in fuel cell we work on platinum. And we have also the second problem is the poisoning of the surface of the electrode. We have also the time of synthesis of catalyst and also the stability of the catalyst. So what we do is to replace platinum by nickel or copper, and the first work was done with methanol, and we use for that we use paraphenyldiamine with carbon nanofiber and nickel nanoparticle, and this is the characterization of the surface of the electrode. When we use carbon nanofiber with the polymer, we can see the polymer on the carbon nanofiber. And after that, here is the oxidation of alcohol. There is no response on the carbon, on the bare electrode, but there is very good response when we have carbon nanofiber with nickel nanoparticle and phenylendiamine. And what is the role of the polymer? When we have the polymer, we ensure a good dispersion of metallic nanoparticles on the surface. We have also a high surface area, and we have very good stability here. The stability, is here, and we have stability above 6 hours, and we compare, of course, this with platinum electrode. Another polymer who was used also, it's copper, also copper with paraphenyldiamine, and here we use cascade reactions. The prepared electrode was prepared by domino reaction in one pot synthesis, in one step. So we put together copper with polymers, And this is the mode of preparation. We can use potentiostatic mode or galvanostatic mode, and the response is very good compared. This is different morphology of the film using potentiostatic or galvanostatic mode, and the film is prepared in 10 minutes. And here we have the response of ethanol compared to copper alone, copper using potentiostatic or galvanostatic mode, and the electrocatalytic performance of our developed electrode is given on the table, and we have a very high response of ethanol on copper modified paraphenyl diamine. And of course, we have to test the stability of our electrode, and here we can see the stability of different electrodes prepared in different manners, and we have stability after 700 cycles. So if you compare our results with the results in the literatures, we can see that our sensors is prepared only in 10 minutes compared to other sensors prepared by other authors. And the last part of the work, and we started this, we have just submitted our article to nanoscale, is about applying our catalyst for splitting water. So for splitting water, in the cathode we have production of hydrogen, and in the anode we have production of oxygen. And we need also catalyst, and the best catalyst used until now is platinum electrode. And we see together platinum is very expensive. So the challenge is to develop new materials with the catalytic performance such as platinum, with low overpotential and with large ion density. And for this, we will use transition metals such as nickel and copper oxide or hydroxide to see what will be the response of this kind of material toward hydrogen projection. I will give you some response that we have had very, very recently. It's about modification of the surface with paraphenylene, polyparaphenylene diamine, and also with bimetallic nanoparticle, nickel and copper. And we compare different polymers. Here we have the response of orthophenylene diamine, metaphenylene diamine, and paraphenylene diamine. And the best response was obtained with paraphenylene diamine combined with nickel and copper. And we can see that the overpotential is around 260 millivolts. But after optimizing all the parameters, we have reached a value, here it's over potential, we have reached a value of 70 millivolts, which is very good results in splitting waters. So with nickel and copper as combined with phenylene diamine. So our catalyst or our nanocomposite or our nanoenzyme were evaluated as electrochemical sensors and also as catalysts for direct alcohol fuel cell and splitting waters. Also, further study in our group are underway to understand the mechanism and also to exploit this nanocomposite for energy storage application and hydrogen evolution reaction. Thank you for your kind attention, and I have to acknowledge all my PhD students. Thank you very much.
Thank you. So the time for one question.
Okay, thank you for your work. My question is about the morphology of, you are presented some results concerning the surface area.
Yeah.
But what about the morphology?
The morphology, it depends what we want. For alcohol oxidation, for polypyrrole and copper, if we have a polymer with high conductivity, we can change the morphology from cubic to nanodendritic. And when we have nanodendritic, we have more active
sites. Okay.
More active sites, yeah.
Okay, but how do you control this, the change of?
We control it by time of deposition and also by having a best polymer in substrate, as substrate, before deposition of.
So why do you use at that time the metal? Why do you use metal nanoparticle if you just control the morphology of the?
For ethanol and methanol, we should have metallic nanoparticles, but the resistance with metallic nanoparticles without the polymers is less than.
Okay.
And I think that I passed that. Yeah.
Okay. Okay. Thank you.
Oscar separately, yeah.
By electropolymerization, by electropolymerization using cyclic or galvanostatic or
Viens, mon ami.
I think take this up afterwards, yeah, because this is too awkward a question. Yeah, because we are running late. Okay, our next speaker, I'll pass over to you.
C'est là-bas?
Yes, yes, you can take your computer.
Ouais, vous pouvez me permettre? Je vous le remets à la fin, s'il vous plaît. Ça fait depuis hier que je leur demande s'ils ont un pointeur. Parce que...
Vous avez travaillé avec le PC.
Mais ça.
Ok, donc vous le branchez sur le truc.
Oui.
Je dois changer les piles, moi. Ça, c'est pour le.
C'était comment?
I will first of all like to thank the Professor Modou-Fall for inviting me here for this conference. My talk deals with the opportunity given by electrochemical tools for the analysis of solution, and specifically in this work, we are going to analyze caffeic acid on carbon electrode modified by a clay, this clay being functionalized by an ionic liquid. So, okay. So we are going to analyze caffeic acid. Caffeic acid has very interesting property due to the presence of the catechol group. And these applications are in cosmetic, drugs, food preparative, and this caffeic acid has antioxidant property, anti-cancer, anti-inflammatory property. I would like to emphasize on the fact that caffeic
caffeic acid is mainly in the anionic form as far as pH is is more than 4.41, and as you can see in this speciation diagram, caffeic acid, when we are after pH 4, is mainly in the anionic form. Why are we interested in quantificated caffeic acid? Because, as I said, they can permit the control during synthesis. They can be quantified in food, tea, coffee, and in health diagnosis. As far as analysis is concerned, the technique which is frequently used for the quantification of caffeic acid is chromatography. But as you know, chromatography needs a long time of analysis and is consumable for products. By contrast, electrochemical techniques are simple, use affordable equipment, are fast, and can provide high sensitivity and precision. But electrochemistry also have some limitations, especially the poor sensitivity of conventional electrodes. That is why these electrodes have to be modified to permit a high sensitivity. In our case, the electrode is modified by a clay material. The clay material used is haulusite, which is a tubular clay mineral with layerless structure, but which have poor reactivity due to the fact that, as you can see here, the interlayer does not have any ion. It can be dehydrated, or if you have water in the interlayer, it's hydrated haulusite. So this clay also needs to be modified to induce new properties. Previous works on kaolinite, which is a clay structurally close to haulusite, show that selected ionic liquids can be quantitatively graphed in the interlayer space. In this shape, you can see that we can insert an ionic liquid between the layer of the kaolinite. The cation is an organic cation, and we have an anion. When the organic cation is graphed, the free anion could be exchanged. That is this property that we are going to use to functionalize our clay. So, the main objective of the work, as I said, is to functionalize this clay with an ionic liquid to obtain an anionic exchanger material and then apply as electrode material for the CA detection. I would like to emphasize on the fact that the selected ionic liquid should be bulky enough to allow the CA to come into the interlayer of the clay. In this work, we have chosen this ionic liquid that I will be referred to as NIM, with this organic part, which is the cation, and Cl minus the anion. The modification scheme is like this. You first have a first step, which is the pre-intercalation by DMSO. Then you obtain the clay DMSO, and in the second step, you can draft your ionic liquid to have clay ionic liquid. Then, after you have obtained this, you just have to modify your electrode by drop coating, and then in a classical accumulation detection, well known, you can do the application. But first, we have to be sure that we have graphed the liquid, the ionic liquid in the interlayer, and we have checked this by XRD. We notice that the D001, well known, has been shifted from 072 to 179 to show that we have expanded the interlayer. Second, we have to be sure that the clay modified by the ionic liquid conserve the same structure. That is what we have been verified in this C13 RMI. And lastly, we have using thermogravimetric analysis to know the quantity of the ionic liquid that has been linked to the clay. Okay. So, you can see on this scheme that the signal of the caffeic acid is by far more intense when you use the clay modified electrode which is graphed with the liquid ionic compared to the glassy carbon himself. You can even not see anything. Even when the glassy carbon is modified by the clay only, the signal is very poor. But when you use this glassy carbon modified by the clay, which himself is modified by the ionic liquid, you can see this signal, which allows us to detect the caffeic acid. After that, we have tried to optimize the process by checking the optimal pH value, the optimal accumulation time, and to see the peak variation for electrode repeatability. A calibration curve for CA concentration ranging from 0.05 to 1.5 micromole show that the sensitivity and the detection limit is very interesting. We have then compared the performance of our modified electrode with conventional electrode found in the literature, and we see that our electrode behaves very well. We also try to see if you can determine in real sample caffeic acid. So you can see in this scheme that you can. Yes, I will. See a determination in T and two variety of T. So by functionalizing an electrode with an ionic liquid, we can reach to a fine determination of CA. Alusit was effectively modified and the ionic liquid graphed in the interlayer. We used this modified electrode to analyze CA, and the sensors show a very low limit detection and efficient in determining C in T sample. I would like to thank ANEC, that is a network of African electro-analysis chemists, my university of Yaoundé Wine, my lab, and also, as I say, when I begin, to thank the Senegalese Society of Chemistry. Thank you very much. Merci. Okay.
You have just to press here. Okay.
Okay, thank you, Mr. Chairman. Good afternoon, everyone. I am Muhammad Muzakir from Department of Chemical Science, Gombe State University, Nigeria. My talk today is on the fissile electrosynthesis of titanium nanotubes incorporated by binary nickel manganese oxide as hybrid supercapacitor electrode for sustainable energy storage. So I want to follow this presentation outline. First of all, supercapacitors are electrochemical energy storage device that can store energy on an electrolyte interface via two different mechanisms. The first one is through what is called electric double layer capacitance through ion absorption desorption on the electrode surface. And then the other mechanism is based on the reversible surface redox reactions that are called pseudocapacitance. Titanium nanotubes, they are 1D nanostructure materials that possess high surface area and can provide short diffusion pathways for electron and electron transfer, while the nickel manganese oxide are mixed transition metal oxides that have a cubic spanner structure. They possess high redox active sites that can be served as a promising material for pseudocapacitance. So what's the problem? We are interested in these supercapacitors because of these problems. The first one, as we know, we have depletion of fossil fuels and the worsening environmental pollution, also increasing in energy consumption due to growing population and the technological advancement. So renewable energy sources can solve some of these problems, but there is major problem in using the renewable because they are intermittent in nature. That means they are not continuous and they depend on the time and area. So there is need to find a way of storing the energy as soon as you produce so that you can use them subsequently. Supercapacitors, as one of the energy storage devices, they bridge the performance gap between the traditional capacitors and also between the batteries and the fuel cells. Supercapacitors, as you can see from this graph, as you can see, supercapacitors, they are in the middle, so they have high power energy greater than batteries and also high energy density greater than the capacitors. So these are some of the specifications. They have high power density, typically between 60 and 20 seconds discharge time, and also high capacitance up to 1,000 farad. And also excellent reversibility, usually 90 to 95%, and most importantly, long cycle stability. And also they can work within a very wide range of temperature from minus 40 to about 70 degrees centigrade. The global market for supercapacitors is increasing, as we can see from here. From next year, 2025, it is projected that the global market is going to hit 8.3 billion US dollars. And by this side, we can see that we have various applications where we are using supercapacitors. For example, in the mobile power sources, fast charging vehicles like electric vehicles and the hybrid vehicles, also in wearable biosensors and power sources, also in building power source. All these are some of the applications. So for this project, I have these following objectives. The first one is to optimize the synthesis of titanium nanotubes by electrochemical anodization, also to incorporate nickel manganese oxide into the titanium nanotubes using pulse electrodeposition, then to characterize the material, and also finally to evaluate the electrochemical performance of the synthesized nanotubes. These are the methods we use. The first one, we have the titanium foil. So in this case, we are using titanium foil to synthesize the nanotube. And the titanium foil serves as the current collector. So you don't need to use a binder to now bind your material onto the substrate. So you can directly ground the nanotube on the substrate, which is the titanium foil, and it also will serve as the current collector. So we use anodization methods using glycerol, ammonium fluoride, and some mixture of water. After optimization, this process takes about 60 minutes to have our titanium nanotube. And then after that, we calcine at about 500 degrees centigrade under air atmosphere for about 2 hours. And then we get our titanium nanotubes. And then for the incorporation of the nickel manganese oxide, we use pulse electrodeposition. And after optimization to about 6 minutes, we got our nickel manganese oxide deposited on the surface of the nanotube. And then at the end, we carry out electrochemical evaluation in 1 molar potassium chloride using the CV, cyclic voltammetry, GCD, and then the EIS. So these are the results. The first one, these are the extraordinary results of the titanium nanotubes before the calcination and then after the calcination. We can see that before the calcination, we don't have the anatase phase. Then after the calcination, we have the anatase phase at 101. This is the extraordinary result for the titanium nanotube, and then after the incorporation of the nickel manganese oxide, after the incorporation, we have a peak around 311 and also around 311 and also around 440 that indicate the presence of nickel manganese oxide. We further characterize the sample using the XPS. The first one is the general wider survey for the sample. We have the presence of the nickel, manganese, and also the titanium, and then the oxygen, and then the second spectra is that of the titanium 2P, where we have a peak at about 458.8 electron volts, which indicate titanium 2P peak. Further, we also have the peak for manganese 2P and also that of the nickel 2P. For the manganese 2P, we have, shows the presence of different oxidation states of the manganese, like manganese 2, manganese 3, and also manganese 4. And then for the nickel also shows different oxidation states of nickel 2 and nickel 3. Then this one for the O1S spectra, we have a peak for the metal oxygen and then a peak for the metal hydroxide, and then a peak for the water. So this is the morphology of our samples. The first one is the titanium nanotube before incorporation of the nickel oxide. The first sample is the surface morphology, and then we also have the aerial vertical morphology, as you can see. The average tube diameter here we have 86 nanometer and average tube length 1.7 micrometer. Okay. Okay. And then the average thickness of the tube is 21 nanometer. So this is the after incorporation of the nickel manganese oxide. As you can see, some deposit on the nanotube diameter. And these are the electrochemical studies. We have our CV for the titania and then the GCD. And then this one, after incorporation of the nickel manganese oxide, the CV, we have redox peaks, as you can see, and also we have the GCD. This is the stability study. We studied the stability for 2,500 cycles. And we have a very good stability after 2,500 cycles. So this EIS study to know the resistance between the interface, we have a very low cell resistance and also that of charge transfer resistance. So in conclusion, we have synthesized these titanium nanotubes via simple, fast, and cost-effective method, and also incorporated the binary nickel oxide into it to improve the pseudo-capacity performance of the sample. The capacity performance of this sample was remarkably increased by about 42 times to about 97 millifarad per centimeter squared after incorporation of the nickel oxide with very low equivalent resistance. And also, furthermore, the sample exhibits a very electrochemical stability and rate capability by retaining about 96% of the initial capacitance after 1,000 continuous charge. Thank you for your attention.
Thank you very much.
Okay.
Yeah, we're trying to get through because otherwise we're not going to have much before 2. Trying to get through because we've got 5 quarters to go. Right, so
PDF lah. Ya.
Yeah, good evening, everyone. I am Dr. Balafal from Cheikh Anta Diop University. It's a great honor and pleasure to share with all of you one part of my work entitled Electrochemical Sensor, based on the CNT MOS2 FO2O3 material modified glassy carbon electrode and application to the sensitive detection of mercury ions in tap water. The plan as follows. After an introduction, we will present the material and methods, and result and discussion, and to finish by a conclusion and a perspective. In introduction, mercury, silver white is a well-known hazardous metals. It generally occurs in mercurous, elemental, or alkali form in nature. The redox potential and the pH of the system are responsible for its stability. It is frequently used in thermometer, barometer, nuclear reactor, etc. It comes from natural or human activities, and mercury is spread over the globe through the atmosphere and through the oceans. Once present in water body, mercury is readily converted into organic mercury compounds that are more easily taken by animals, and therefore more dangerous for the health and humans. The impact of mercury. For humans, we know that acute exposure to mercury can have adverse effects on brain damage and other diseases. Therefore, it's necessary to develop a method. It's necessary to develop a method. First of all, a spectroscopy method have been developed. This method were stable, efficient. However, this method needs qualified person, heavy equipment and high cost, relatively long analysis, and it's impossible to carry it out on site. Alternatively, electrochemical methods have been developed. This method is simple, fast, reliable, low cost, gives the possibility to modify the surface of electrode and to do the simultaneous detection. The aim of my work is to develop a new, highly sensitive, reproductive, and selective, stable, and efficient sensor by making MOS2, the two-dimensional nanomaterial, due to its mechanical, electrical, catalytical properties, and combine CNT, MOS2, and FO2O3 to design nanomaterial with superior properties. For this work, the chemicals, equipment, and method are presented here. The overall synthesis process is present in the figure 1, and the analytical process in the figure 2. First of all, we have studied the effect of experimental variable, electrolyte, peak position and intensity are highly dependent on the carrier solution, the pH of solution. The redox potential is very sensitive to the pH and has a significant influence on behavior. The deposition potential significantly increases ion reduction and density increase. The deposition time enhances the quantity of ions reduced and therefore current density. The pulse amplitude for the resolution and peak shape, and the potential step for the peak height and wide. All experimental variables are presented in the table 1. And after gradual addition of mercury, we note an anodic peak around 0.2 volt attributed to the oxidation and reduction of mercury during pre-concentration, a gradual increase in electrochemical signal with mercury ions, and a linear dependence of current density with the concentration of mercury. Hence, it is possible to use this material to detect mercury ions in water. The electrochemical performance of the sensor is given below in the table 2, and after analysis of the table, we noted the LOD below the WHO tolerated concentration and a high sensitivity. Due to this, which can be explained by the sensor is a good candidate for the mercury ions electroanalysis. After then, we have tried to study the interference effect, and we know the mercury are frequently causes in natural environment with other metal cations, which can occupy the depositional or coordination site available on the electrode. This can decrease the signal of intensity and disperse analysis, or the formation of an interferent film, metal film, leading to easy reduction of an highly signal level. And after addition of different metal cations, we note a gradual decrease from 0.1 to 13% for mercury signal, which can lead the low interference effect. And when we add the copper ions, we note an increase of the intensity due probably to the formation of AgCu allow or proximity of signal. And in order to evaluate the performance of our sensor, we try to detect mercury ions in tap water, natural water, And without addition of mercury, no electrochemical signal. This can be explained by the extremely low concentration of mercury in medium. And after fortification with various concentration of mercury, we have a signal, electrochemical signal, proportional with the concentration of mercury ions. In order to understand, we try to calculate the recovery rate, and the recovery range from 97 to 150%, and the standard deviation is lower than 8%. Hence, this method is accurate for effective detection in mercury ions. In conclusion, we have successfully, for the first time, to synthesize this material and apply it to the detection, to the electrochemical detection of mercury ions. We obtain we can detect a low concentration of mercury ions with a LOD of 0.015 nanomolar. We note also a low interference effect and a satisfactory result when analyzing 45 real samples. In short, we have a new, low-cost, easy-to-use, high-sensitive, efficient, and stable sensor for monitoring trace of mercury ions in the environment. This work opens some prospects like to apply our sensor to the detection of caffeines, glucose, or other molecules, organic molecules, or to apply this material for the support, capacitor, or fuel cells application. Thank you for your attention.
Allow you one question, we should check a bit of time. Yeah, sure.
Yeah. It's not presently here, but it is in the figure 3. Yeah, it is. Is it nanomolar? Nanomolar concentration. Yeah. Yes. Yeah. Very low concentration. Yeah. Thank you.
Okay, thank you. Right, so thank you very much. Right, our next speaker is Jabel Sal.
Yeah, it's me. Yeah, it's me. Yeah, thank you, Balafal, for the presentation. Good morning, everyone. My name is Jabel. I'm a PhD student. I'm working with Professor Abdou Karim Gandiaw here in Senegal and Professor Miliana Emadi in French. I'm honored to be here to present in my work entitled Amperometric non-enzymatic determination of glucose via a glacial carbon electrode supported with carbon nanotubes, molybdenum disulfide nanocomposite, and nickel nanoparticles. Now you know a bit about me. Let me delve into the outline of my introduction. First of all, here I will start my work by explaining the art of my work, giving firstly the context and the procedure for synthesis of my nanomaterial. And after, I will give the result by some characterization by FTR and ECM and the procedure of electrooxidation of glucose and the glucose detection with amperometry. And I will finish by conclusion and work in progress. Diabetes is the most chronic non-communicable disease and is regarded as the worldwide epidemic. It is characterized by blood disturbance resulting from insulin secretion or insulin action. In 2017, it affected 425 million people in the world, and this number will go at 629 million in 2020. In 2045, this is why we want to create a new enzyme for determination of glucose. And our aim is to use the glacial carbon, and here we will use the glacial carbon electrode, and we will drop cost the nanocomposite carbon nanotubes disulfide molybdenum, and after we will do the electrode deposition onto the surface by nickel nanoparticles, and we will use the sensor for detection of glucose. And for doing that, here we have the procedure. We use the hydrothermal method for doing the synthesis, and after we obtain our nanocomposite CNT MOS2. And we characterize by FTIR, and the FTIR here is used to elucidate the functional group of MOS2 and CNT MOS2. And as you can see in this figure, the picture appears around 650 is attributed to MOS restriction vibration. It is followed by the characteristic absorption band of MOS2 at 900, 1040, and 1060 centimeters -1. In addition to the peak of MOS2, the peak appear around 1040 and 1060 and 1089 centimeters -1 in the CNT MOS2 is attributed to the restriction vibration of COCC and CS bond. And this result to show the MOS2 and the CNT MOS2 has been effectively synthesized. And have been synthesized. Yeah. Here, the morphology of the other obtained nanocomposite was performed by Fossums, and the Fossums image of MOS2 here depict a sticky and significantly crumpled flower-like shape in addition to the flat surface, indicating that MOS2 is formed in two-dimensional layer. And however, the CNT MOS2 image show a structure where the MOS2 are uniformly implanted in the CNT network, indicating the creation of three-dimensional hybrid network from the interconnection of the MOS2-wrapped carbon nanotubes. And in order to confirm the composition of the CNT MOS2 nanocomposite, energy dispersive X-ray EDX analyzer were performed. And elementary mapping of the ECM image of a selected area reveals a peak of C, O, M, O, and S, showing clearly that the nanocomposite is mainly composite of this element. And this result is an indication of the high element purity of the synthesis of material. And then we studied the electrochemical behavior, and here, as you can see in this figure, the A, in the absence of glucose, there is a pair of well-defined redox peak. And we can see when we added a glucose, there is a gradual increase as a function of glucose concentration, and as well as a slight shift of anodic peak toward high potential. And this shift is mainly due to the division limit of glucose on the electrode. And this result indicates that glucose had been oxidized via a mediated redox process. And this process is following here. Here, the oxidation of glucose to gluconolactone is catalyzed by the Ne3 plus Ne2 plus couple, where the Ne3 plus in the surface of the electrode oxidize rapidly the glucose in the anode. And this targets the sensor oxidized glucose and therefore exhibit a good electroactivity performance. And then we study the scan rate and kinetic study. And as you can, and the scan rate here study between 5 millivolts per second, between 5 and 100 millivolts per second. And we can see here we've increased scan rate, the anodic peak potential shifted positively while the cathodic peak shifted negatively, and showing that the electrochemical reaction is a quasi-reversible electron transfer. And in the insert in this figure, both of these peak current density vary linearly with the Escal road. This means the electrooxidation is governed by diffusion process, which is ideal for quantification analyzed in practical application. And after that, we use the sensor now for detection of glucose by amperometric method. And here we can see the noticeable current increment, and the sensor reached the steady state current in less than 3 seconds, indicating a quick response to oxidation of the glucose. And the calibration curve show a good linear relationship with glucose concentration over a broad range of 0.05, 0.65 millimolar. And it's so sensitive, and the detection limit was 0.2 micromolar. And this detection limit is compared with others in the literature. And we can see here, we can say here, our sensor exhibit electrocatalytic activity, a good electroactivity, and also a broad linear range and a short response time, a short response time like 3 seconds. And this is due to the, and this result is due to the interaction and the synergic effect of the separate compound, including carbon nanotube, disulfide molybdenum, and nickel nanoparticles, who give the sensor its exceptional performance. We also study the interference of our sensor with other sugar like sucrose, maltose, fructose, mannose, glucose, and uric acid something. And here we can see the first signal and the last signal characterized by a large current steep are relative to the addition of glucose. And beyond that, no appreciable response was observed. It's was observed. And remarkably, despite the addition of the interference species, the response of the final glucose addition have a value similar 980% to that for the first glucose addition. It means the present electrode exhibit excellent selectivity. Also, the stability also is a study, and here the amperometric current response to glucose over a day, and we can see the current density are approximately 89% of their initial value after a day. And these results demonstrate the great potential of electrode in glucose sensing. And after doing all of this, we use our sensor to measure the amount of glucose in energy drink 3X sold in Senegal in order to evaluate the applicability of our method. And prior to analyze the sample, was suitable diluted with water to ensure that the glucose concentration were within the linear working range and to minimize the potential matrix effect. We decide to use the curve produced after tenfold diluted, and after calculate, we have our concentration was 1.96 millimolar, and this concentration is lower for the recommended limit between 3 and 8 millimolar. And this means our sensor is exceptionally sensitive, and this finding indicate that our approach is sufficiently accurate and appropriate for determination of glucose. And in conclusion, we were able to successfully synthesize our nanomaterial and characterized by FTR and fluorescence. And after the catalytic activity was investigated by cyclic voltamperometry and amperometry measurement in alkaline media, and the synergy effect of the nanocomposite and nickel nanoparticle sufficiency boost to the electroactive for the glucose oxidation. And the electrode is high sensitive, have a low limit detection and wide linear range. And the signal generated by oxidate is unaffected by other species. Finally, the sensory result to measure glucose in real samples. As a result, it can be used as a non-enzymatic glucose sensor. And we plan to use carbon dots to detect glucose by fluorescence method. And we have synthesized the carbon dots using citric acid and ethylene diamine. And after we have doing some characterization like XPS, XRD, FTIR, and some spectroscopy, and also the detection. Thank you for your attention.
Sample application, and you talk also about that. This means visualization page. However, what we did here is an archive page, 01 normal. So you can never apply such a level of visualization calculation. This is one. The second thing, one could say it's difficult to how you explain that, because there is no big difference between galactose and glucose.
Yeah, there is no.
How do you explain this?
But I can explain that because here I can. Yeah. Okay.
We've got 2 more talks. We've got a blind stone, and then afterwards we've got S26. So you will come afterwards. So 2 more talks, and then we've got
Chico. Thank you very much. Ladies and gentlemen, dear professor, it's a pleasure for me to present to you a part of my research result into synthesis and characterization of electrochemical properties of a new gel polymer electrolyte for energy storage device application. My presentation will follow the plan. First, we do an introduction, followed by the methodology, result, and discussion. And finally, we give a conclusion. I would like to start by presenting advances in electrolyte. It is important to note that one of the main interesting component of electrochemical energy storage devices is the electrolyte. And the electrolyte ensure the ion conduction and allow charge storage in electrochemical device for energy storage. The commonly used electrolyte for this device for energy storage is liquid electrolyte that, despite their interesting properties, meet some issues such as the inevitable dendrite growth, low safety, poor electrochemical stability, and leakage. So these issues compromise their use in some field. So it is necessary to experiment other electrolytes such as solid polymer electrolyte and gel polymer electrolyte. Among the two, the gel polymer electrolytes are more promising for energy storage. That's we judge necessary to prepare a new gel polymer electrolyte for energy storage application. For that, we have synthesized the gel polymer electrolyte by mixing in an aqueous solution of potassium chloride. We add tannic acid, PVA, polyvinyl alcohol, carboxymethyl cellulose, under two parallel steps using sonication and magnetic stirring. And we have finally our gel, named CT80K gel. For studying the electrochemical properties of our conductive gel, we realized the study considering two device samples using ITO, indium tin oxide electrode, at different surfaces. Cell 1 used ITO for a surface of 25 centimeters square, and the second sample used ITO for a surface of 100 centimeters square. And the method we use to study the electrochemical properties of our conductive gel is the electrochemical impedance spectroscopy with experiment condition noted as below. System configuration to electrode, room temperature for the experiment, frequency range from 100 kilohertz and to 10 millihertz. The working potential is 0 volt and the sinus voltage amplitude are taken for 5 millivolts. From the complex capacitance obtained by the electrochemical spectroscopy impedance, let us plot the evolution of the imaginary capacitance as a function of the real capacitance. And here, the real capacitance allow us to determine the storage capacity of this device, and the imaginary capacitance allow us to determine the loss of capacitance in the device. So here, the curve obtained, the curve obtained, let's see at a low frequency, a semicircle where the geometry corresponds to the storage capacitance. And to better study the difference between the two responses with the two devices, we have plotted separately the evolution of each capacitance as a function of the frequency. And here at figure 2a, we can see the evolution of the storage capacitance as a function of the frequency. And here we can see a net difference at intermediate frequency. As we can see, so this difference at the curve 2b, at intermediate frequency, we see a net difference of the two responses. And here we see a peak
for each device, and the value obtained with the two figure let us give the capacitance stored and the loss capacitance for both cells. And here we can note that the capacitance stored is greater for the device using a low surface, and for the capacitance for the device using a higher surface electrode, we note that the loss capacitance is very important. And here we see that the imaginary capacitance, let's see a frequency peak at 13.2 Hz for ITU using the low surface electrode. And for the higher surface electrode, we see a peak, a frequency peak at a low frequency, at low value. And this can inform that the low ITU surface-based cell need shorter time to be charged. So the difference we see in the two capacitance is due to the presence of resistance. And here we can find this resistance by plotting the evolution of the real capacitance as a function of the real impedance and the intersection of the curve and between the curve and the x-axis lets us register the resistance. And here we have the two values for the cell using low surface. We have resistance, a low resistance at 110 ohm centimeter square, and for higher surface we have a higher resistance. So the conductance is important for dispersion study of electrode surface. And here we plot the evolution of the imaginary conductance as a function of the real conductance, and we see a net difference of the curves. And to better analyze this difference, we plot the evolution of the real conductance as a function of the frequency. And this allows us to register this value. Here we can see that the conductance is very important for the device using ITO with low surface. After the determination of the conductance, it's important to determine the conductivity of our conductive gel. And the importance here is that the conductivity takes account to both electrode surface and cell thickness. And using this formula, we find a value of the conductivity higher with the ITO using surface, low surface. So here, the higher value of the conductivity found with the ITO using low surface is due to the mechanism of mass transport. Here we can note that the transport is provided by migration, because we are more the capacity, the surface is higher, more the uniformity of the electric field is lost. And this provides that the driving force is due to a potential gradient. That means that so the difference of value is due to a migration phenomenon. In conclusion, the specific capacitance resulting from cell study remain constant and non-dependent to electrode surface variation. It has been noted the influence of electrode surface on electrochemical properties of the gel. The lower electrode surface, the higher specific capacitance and then ionic conductivity of the gel increase. The mass transport in the conductive is ensured by migration phenomena. The highest ionic conductivity is the 0.114 millisiemens per centimeter, and this result from our conductive gel shows that it can be a good candidate for energy storage device application. Thank you for your attention.
So afterwards, you can bring up the questions. We've got one more talk, and then we're going to go for lunch, and we'll have the other talk straight after the CAS talk. So CAS talk is a Zoom talk, so we've got to keep to that schedule, and then we've got plenty of speakers straight after that. So we've got one more speaker, moved from S2C26, Sapakazi Temakwe, and she's going to talk now.
Is it your first time on Sasa? Okay. Show it. The screen? Yeah. Wait.
I'm saying it's not showing there on the screen there, where people see. Look at the screen up there. Good day, ladies and gentlemen. I am Sapokazi Dimakwe, a PhD candidate in chemistry from Cape Peninsula University of Technology in Cape Town, South Africa. I'll be giving an oral presentation on differential pulse voltammetry zidovudine biosensor based on silver nanoclay composites modified classic carbon. I'll take you through the background of the study. Okay. I'll take you through the background of the study and the objectives, the method of synthesis and the method of fabricating the sensor, the results and discussion, and also the conclusion of the study. Well, zidovudine is the antiretroviral drug. That is the type of nucleoside reverse transcriptase inhibitor. It inhibits mother-to-child spread. Its demand is high, thus poses as a threat in the environment, and also it has little therapeutic interval that is becoming ineffective with time, causing health complications such as gastric pain, bone marrow, and liver problems. Well, there have been methods that have been reported to monitor the drug quality, such as analytical, which are associated with high cost, longer analysis time, possible loss of analyte during re-extraction process, and also there have been electroanalytical methods that have been reported, which is voltammetry, that uses the film of gold and platinum that are also known to be expensive. Also, polarography method have also been reported to monitor the drug quality, but they use hanging mercury drop electrode, which is known to be toxic or poisonous. Thus now the study, the proposed study uses nanoclay functionalized with silver, and with the use of human serum albumin as a biorecognition element. So nanoclays are used because they are inexpensive, and also they are easily available. And the silver here is used only to enhance the connectivity of the nanoclay because nanoclay is poor in connectivity. So the objective of the study is the synthesis and characterization of silver nanoclay composites, fabrication of the biosensor using the synthesized silver nanoclay composites, also optimization of the sensor of the fabrication method, optimization of the procedure, validation of the biosensor, as well as the application of the biosensor. So I've synthesized nanoclay composites using 0.5 grams nanomar, which is the nanoclay, and added in the solution of silver nitrate. The mixture was heated for 20 minutes at a speed of 265 RPM, followed by the dropwise addition of 4 mil 10 millimolar of trisodium citrate as the reducing agent. The mixture was continued to heat for 15 minutes, and after that it was cooled to room temperature. So the product was cleaned through centrifugation for 5 minutes, 3 times, and was collected. The collected product was characterized with spectroscopic and electrochemical techniques. However, I did not show the results here, but I do have published papers on the characterization. So the fabrication method involved drop coating of the synthesized composites on the clean glass carbon electrode and allowed to dry for 26 minutes, followed by the drop coating of human serum albumin and dried further for 15 minutes. So the sensor was used to detect the zidovudine using the 3 electrode system. Well, after that, we have optimized the sensor fabrication method by firstly changing the way we are introducing the human serum albumin. That is, we have drop coated and immersed. So we checked now the connectivity, the response of zidovudine, whether it's high in when HSA is drop coated or when it's immersed. So we found that now the drop-coated HSA gives higher signal of the zidovudine. From there, we've optimized the concentration of the electrolyte, that is the PBS electrolyte solution, whereby we found that now the 1 molar PBS of electrolyte is the best option due to the higher connectivity that we have obtained of the zidovudine. After that, we have optimized now the drying time of the human serum albumin to check now if there's going to be any effect. So now we found that after 15 minutes, on 15 minutes, we got like a bigger or a higher signal of zidovudine, and then it slowly decreased as the time of the drying increases. From there, we optimize now the method whereby we optimized step potential, modulation amplitude, modulation time, interval time, and the electrolyte stirring time. So we found that now the values here that I've indicated with red are the optimum conditions of the method that I have used now to calibrate. So now we've calibrated using the optimum conditions, and then we found that from the calibration, we were able now to calculate the limit of detection of the sensor that I've developed and compared it with the previous studies. So we found that now this limit of detection that I've obtained is lower than the one that was obtained previously from it's higher than the one obtained for that was reported for hanging mercury drop electrode. But because of what I have said or I've mentioned earlier that it's poisonous, therefore the one can be used as an alternative. Then we validated the sensor and also used the sensor in real commercial tablets. So now we've used ascorbic acid, citric acid, and glucose using in different ratios. So as you can see now here, when now zidovudine is high in the solution, we get the higher signal of it. But now, as now you introduce now the other interferences, we see now we can still get the zidovudine, but there's a slight decrease. Also, we have also checked now the interference using the other ARV drugs, but I must say that I have not seen a study on ARV, or I mean, I have not seen zidovudine combined with efavirenz or nevirapine, but those were the drugs that were available in the lab. So out of curiosity, I used those drugs now to check if now there's going to be any effect. So we went through and checked the recovery and studied the recoveries, whereby now I've used now urine and diluted it with PBS. So these are the recoveries that we have found, the 95% and 116%. But here, what I've noticed is when the PBS in 1:4 ratio, we found 116% recoveries, and as we diluted it to 114, 1 to 14 ratio, there was 95% of the drug that was recovered. Then in the real sample analysis, we had 3 tablets, real tablets, whereby now we actually dissolve those tablets separately. And now we have used the tablets and added in the electrolyte solution. After that, we calculated now the average of the 3 tablets, whereby now we've got 301.3 milligrams, which is closer to the commercial stated amount of zidovudine of 300 milligrams. Then we also went through and checked the electrochemical parameters of zidovudine, whereby we found that the reaction that takes place or that is involved involves 2 electron 2-electron reaction, and also we calculated the diffusion coefficient and also the heterogeneous rate constant using the Randall-Severs plot, Randall-Severs plot and equation. In conclusion, so the development of the sensor was successful and the optimum conditions were determined. The recoveries of 95, 105, and 116 were obtained. Successful detected zidovudine in the presence of interferences, and the amount of 301.3 milligrams of zidovudine was detected, which is close to the stated commercial amount of the real tablet, and also obtained the 1.9% of the RSD, which is considered to be good, and also, and we can also use this sensor now because of the stated reasons or what we have actually obtained. We can use it as an alternative to the sensor that has been developed of the hanging mercury drop. Thank you.
Also, please, the young researchers who are granted for IUPAC, we have to take a photo with the president of IUPAC. IUPAC grantees, there are 5 persons, Khalidou, Gambia, Bilkisu, Sheikha, Adedi Bigbe, Adesina.
YouTube la.
Okay. 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 Yes. Okay, but is she there? I mean, have you told her that we're running late? We,
mais bu vidéo bi dafa li woon dafa xawoon a jafe jafe ni quoi télécharge mooy vidéo bi oui c'était très difficile pour le télécharger
non du téléchargé kii moom lien bi si kii nga ko envoyé ci mail waaw dama ni kon yéen a ngi doon def mais amu leen lien bi non 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 ñu defoon ni si lien bi bu ñu créé si lien boobu lay démarrer quoi waaw c'est-à-dire am ngeen benn kii lien bi ngeen créé pour assemblée générale la boobu c'est à 17 heures moo taxoon mu bind lii 3 fois hein c'est différent 14h30 bi bokkul mais bu 17 heures bi hein bu 17 heures bi yéen a koy gérer
is the link there?
yeah
And is she there? Is she there? The lady speaker.
ça
yeah
là c'est après le fichier parce que Funeral li urgent mooy connexion bi ci kii bi. C'est difficile à recopier. Mais c'est difficile à recopier. Mais il WhatsApp légui, ça ne marche pas. On essaie le mail, je veux pas qu'on continue à perdre le temps. Mënoo bind fii sa mail sa adresse mail looy def jéppel looy def ni sa jéppel ba pare envoyé naa la ko suba tool si moom du dem envoyé wóoru da nga bind adresse bi rek envoyé ñëwul Modou Fall non mail Modou Fall gisoo lien bi gis nga mail bi vraiment envoyé naa moom mooy def introduction bi après jox ko la parole. Hello, Dr. Veresha. Hello, Dr. Veresha. Can you hear us? Mais ba AG bi moom du ñu am yi problème. Hein? Veresha la tudd en tout cas mi ngi may envoyé ay mail di ma soññi rek. benn participant kan la. Non, elle nous a envoyé des messages pour dire je suis dans le meeting. American Chemical Society. Hein? Alors, Veresha. Moha Cissé. Moi yow. Ah. Oui, kon kii laa ko envoyé.
Kii nga ko envoyé.
Waaw yow kat yaa doon bind.
Non,
waaw mais mail bi kay ci destinataire bi la ñuy dugal yow da nga ko dugal ci code texte bi. Alors donc mais jot nga lien bi quand même. Voilà. American Chemical Society, hein? Bon, moi je vais me connecter voir. Il y a un seul participant. They cannot find her. They say that she is not connected. Mais est-ce que c'est pas elle qui s'appelle Julie de Dakar? Julie de Dakar, c'est vous? Non, Julie. She's not online because
Hello.
Hello, Varisha, can you hear me?
Hi, Prof. Yes, I can hear you loud and clear.
Okay, so I'm going to introduce you and then you'll come on, okay? You're on the screen
Sure.
now.
Okay. Hi, everybody.
Good afternoon, ladies and gentlemen. I'd like to welcome you to this next session after lunch. We are going to hear about chemical abstract services and SciFinder. And our speaker today is Dr. Varisha Dukhi, who you see on the screen. Dr. Dukhi is based in Durban in South Africa. She studied at the University of KwaZulu-Natal, where she was the top student in many of our classes and won many awards. She then continued to postgraduate studies, where she obtained her MSc and PhD from UKZN, and I happened to be her PhD supervisor. She worked on insulating materials for transformers. After she graduated, she obtained a job with ACS International, where she is involved with SciFinder. So she comes and trains our students every year on how to use SciFinder and the latest updates. And today she will address us on the topic. So thank you and welcome, Varisha. Thank you.
Good afternoon, everybody. Welcome back from lunch. Unfortunately, I couldn't be there with you today. I was meant to come here on Monday. I had a small injury. Can you hear me? Everyone can hear me? No? Yeah, so I had a small injury. So,
Varisha, there's a problem with your sound. Just hang on while they fix it.
Okay.
Varisha, try again.
Hi, everybody. Can you hear me? Is it okay?
Varisha, just hang on a few moments while they figure it out.
No problem at all.
They've gone to call another technician.
So if you want to go ahead with the next person and we can have me over next, that's no
We,
problem
we
at all.
can't hear you at all, and it just reverberates.
Can you by any chance hear me now? Is the sound better now?
C'est pas vous? C'est pas moi? C'est pas vous qui... Ici, c'est pas... Non, 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 non. In Ouagadougou, Burkina Faso. He conducted several projects, especially a project financed by the European Union since 2019, and it is our executive secretary of the African Network of Electroanalysis Chemists. Please, Prof, you have the floor. Thank you.
Thank you, Professor Emmanuel, for introduction. I would like first to thank FAST and the Senegalese Chemical Society for invitation. Okay, it's a pleasure for me to talk about the use of electrochemistry. Since this morning we had a lot of presentations using electrochemistry for heavy metal detection, medicals. This afternoon I will show just the use of electrochemical tools for pesticide and metabolites detection in water. Permit me first to introduce, but in order to capture the audience, especially for young students, I will switch in French, but my communication is in English. If you permit, I would just like first to introduce, je vais vous présenter un peu le réseau, c'est le président, le réseau africain de chimistes analystes que nous avons mis en place depuis 2013. Et ce réseau regroupe un certain nombre de pays. In English or in French? Okay, English, okay, not a problem. I can. But nobody understands. Okay, no problem. So this network is involved about some countries like Tunisia. In Tunisia, we have a university of Sheikh Tunis El Mana who are involved in the network. Burkina Faso is my university, University of Kizebo. We have in Senegal, University Sheikh Anta Diop are involved in the project. South Africa, we have Rhodes University. Ethiopia, we have University Addis Ababa involved in the project. And in Cameroon, we have two universities, University of Yaoundé one and University of Chang. The objective of the network is just to create a platform. As you said, in Africa, we have a problem of equipment. So through this network, we would like to create a platform to share knowledge and expertise in electro-analytical chemistry in Africa, to increase exchange student South-to-South cooperation, and to maintain and strengthen the expertise in research in a special domain of analytical chemistry, to encourage female in science, because in Africa, in South Africa, West Africa, we have a problem of female in science. So the network is one of the objectives. We'd like also to encourage the formulation of projects and the idea of local problematic. And finally, we'd like to contribute to sustainable development and the promote of clean environments. In this network, we have a committee board. The chairman is here, is Professor Emmanuel Gambini, is the chairman of the network. In the 5 regions, we have focal points. Professor Modou Fall is a West African focal point. In the East, we have Professor Admassi for the focal point of Ethiopia. In Tunisia, we have Professor Nordin Rawafi, who is a focal point. So, as I said, and for this project, we focus especially to promote the development of electrochemical tool for environmental pollution. Okay, and in each country focalize on each domain. Particularly in Burkina Faso, we focus on pesticide detection. And for this network, we try to develop strategy by conception of biosensor, to improve the performance of the sensor in order to detect pollutant, organic or inorganic pollutant. In this communication, I will focus on electrochemical tool for pesticide and their metabolites. In Burkina Faso, as you know, we are agriculture country, and the cotton is largely produced. By producing cotton, farmers use a lot of pesticide. There are some pesticides used here in Burkina Faso. We have organochloride pesticide. We have organophosphorus pesticides, especially phenyltretinoin, we use largely in Burkina Faso, especially during the locust attack in 2012, we use largely phenyltretinoin that causes pollution in the water and soil. So we are involved with the Minister of Agriculture and Environmental to detect the residue of pesticide in water. So it's particular phenyltretinoin, but the problem, as you know, for organophosphorus is an unstable compound, very not stable, and in few days, this component can decrease or degrade to the metabolite. The more stable one is a 3-methyl-4-nitrophenol. So we try to develop a sensor by using electrochemical chemistry to detect them in water. We have used the standard tool, potential star with electrode, some electrode, especially carbon fiber electrode. Then we use especially the carbon fiber electrode, homemade, on which we made modification in order to increase the sensibility of, okay, several. Okay, so as I said, we'll focus only on the metabolite of phenyltretinoin detection. we can follow the behavior of this component. If we follow the chemical behavior of methyl, okay. If you follow this component, electrochemically we have 3 peaks. 1 peak for reduction of a nitro component groupment here. We have also the oxidation of the phenol group here, the peak 4. And we have the reduction of nitro to hydroxylamine derivative, which is reversible. So we have a possibility to do kind of detection. We can follow directly this component by following the peak 4, or indirectly the peak 2 and 3, which correspond to the reduction of nitro derivative to hydroxylamine component. So by using carbon fiber electrode, it's carbon electrode, we have a problem, as said Professor Mamia, of the pollution of electrode. If we use carbon fiber, we have every time the passivation of electrode, which is illustrated here by the decrease of the peak when we use it in water. So we need to manage how to reduce this reduction with different strategy for detection. We follow first the reduction by using cleaning method, electrochemical cleaning method. We can improve, we can reduce the passivation. Okay, we detect and then we clean the electrode. But the problem, when we realize the same of the macro electrode, we have a consumption of carbon fiber. You see the size of the macro electrode decrease from 12 to 8. So it's interesting, but we will have a problem of stability or maybe of material. So we try to another method for detection. If you see, by playing of the potential, the scanning potential, we start reduction by potential -1 until the oxidation. And if you follow it, you see we have no passivation electrode. Okay? Passivation, we can follow the oxidation with no passivation. Okay? It's possible, but the problem also is the time consuming. So we try another method for detection by modification of material with phthalocyanide components. Phthalocyanide component, electrochemically, we modify the electrode during the CV method. We depose the nickel component on the materials, and then after we can control the quantity of material deposit, and to confirm it, we can follow the peak reduction of nickel 1, 2 to nickel 3. It appears during the electrodeposition process. Then we have the thickness. We can evaluate the thickness electrochemically by integrating the area of the peak. Here we have about 80 nanometer. We can reduce it depending on the number of cycles. Here we're going into 57 cycles during the electropolymerization. Then when we modify the carbon electrode by electropolymerization, we can have, then here is naked electrode, but when we polarize it, we have no fooling of the electrode, then it is stable. And we realize the same, and you see here is naked electrode, the surface, this area is clean, but when we made polymerization, we see with nickel polymer, we have the roughness moved, okay, we're going to 5 nano to its reduction of surface specific when we put the polymer. We follow also the sensibility of electrode, and if you see, from naked electrode, we have for limit of quantification 10, and when we polymerize it, we can reduce the limit of detection with going from 10 to 2.5. Okay? It's not enough if we want to use it in real situation. We need also to improve the limit of detection or limit of quantification. This method is directly detection of the oxidation peak. As I said, we can also follow the reduction of nitro derivative to ethoxylamine, the peak 2 and 3, using the two materials, naked or polymerization. You see the specificity of electrode increase twice from the naked carbon fiber electrode. So this polymerization with this component can increase the specificity of the material, our sensor. Okay? And we follow, we follow the modification by using nanoparticle, gold nanoparticle, deposit electrochemically by CV. Then we have a reduction of gold chloride to nanoparticle. We follow with identify, we characterize the electrode surfaces by electrochemical impedance spectrometry, and you see from scanning from naked electrode, we have the resistance capacitance is bigger than those who obtain with modification the material. Okay, so we increase the conduction by adding the deposit nanoparticle, gold nanoparticle in the surface, carbon surface area. We realize then the morphology to see the appearance of carbon electrode after deposit of nanoparticle. How you see, by CV, we have an agglomerate of gold nanoparticle. This makes that this component, this material are not stable. So we need to change the method of deposition by using chronoamperometry. Then you fix the potential or current, and we can reduce the size of a nanoparticle, gold nanoparticle deposited on a carbon fiber electrode. Then we also optimize the chemical process time, and after we have the calibration curve. And if you see, you can easily have a reduction of a limit of detection. Then you remember that for naked we have a limit of detection of 10, but when you use gold nanoparticle, we can reduce a limit of quantification of 0.4, which for us it's better because we can use it in a real situation. We also try to mix the modification surface modification first by gold nanoparticle and then nickel phthalocyanide polymer in order to increase the durability of our sensor. When we made it by electrochemical, by CV or by chronoamperometry, and the polymer we put it on electrochemistry, cyclic voltammetry, you see, we protect our gold nanoparticle, but the problem is the limit of quantification if it increases comparatively to gold nanoparticle. This is normal because we put a polymer on the surface area, maybe the diffusion, the material diffusion can reduce. This is the two methods. Directly we can detect the metabolite, or indirectly we can detect the metabolite. The second method is to realize, molecular imprint polymer to detect also 3-methyl-4-nitrophenol. The process is well known, it's described now. We use only a polymer, it's the monomer is orthophenyldiamine, mix it with our template by polymerization, and then we remove the template in water, and we have we have our material with cavity, with some porosity. We can have this kind of cavity in the material with the electrodes. And we use this with sensor, modify the imprint molecular imprint polymer, the MIP, to detect, to detect the 3-methyl nitrophenol. This is the process when we made this, the same during carbon liquid and after polymerization and extraction, we have this kind of materials. And when we use this sensor to detect methyl parathion, this is the blank, but when we put 10 microgram per liter of metal, we have a peak of reduction of nitro derivatives. We try to follow the kinetic parameters like the pH, the amount of template, the nature of the polymer to have a stable or a sensitive material. Okay? And we use it to detect, to confirm that you made a MIP without the template. We have a non-imprint polymer. So we made the polymerization, we made the template, and we use it to detect the 3-methylphenol. When we compare, this is the NIM and this is the MIP, you see that the presence of template created some cavity on the metal electrodes. Okay? Then we optimize all the parameters, the number of cycles, the amount of orthophenylene diamine, the pH of the buffer solution, and we use this parameter to establish the calibration curve with a limit of reduction is close to 520 microgram per liter. The interference are studied, and if you see, we use methyl parathion and phenitration. This is the pesticide, the metabolite, and the pesticide, and you see we have no interaction. Then the cavity is properly for NMP, 3-methylphenol. Then we can use it to detect methyl parathion in the presence of on phenylnitrophenol in real solution. Okay. And the second component on which we work is diurion. Is an organophosphorus derivative. No, it's not carbazine. Okay, and herbicide used also in Burkina Faso. But on this material, we use carbon passed electrode modified by oxide, zinc oxide nanoparticle. We mix it and we have a sensor. We are very sensitive to detect in oxidation. We have the signal of the detection. We have oxidation of a nitro derivative. We can follow the mechanism and so on and so on. We establish the calibration curve, and actually we try to use it in real solution, in real media, because this herbicide is used in Burkina Faso actually by farmers. So we try to follow in comparatively with analytical chromatographic method in order to confirm our data. Okay. For conclusion, just to say that with the use of electrochemistry, electrochemical tool, we can easily make new tools by modification of material with polymer, with nanoparticle. We can have sensitive tool to detect pesticide and also biometabolite in real solution. This work in continue. Actually, we work on another pesticide used in Burkina Faso. Then before leaving, I would like to thank all the partners, especially OPCW, who supports, and International Science Program, who is a financial support from the network, as I said, the African Network Electrochemists we established. Thank you for your attention.
Thank you so much, Prof. There is time for some questions, if any. Okay. Yes, yes, Prof.
Okay. Thank you, sir, for this nice conference. Well, I have just one question concerning detection at -1 volt. Is there any -1 volt
Yes.
for nitro?
Nitro
There
derivatives.
is no competition with hydrogen?
No, but we bullet the solution. We
Are you,
bullet before.
okay.
Nitrogen, NO,
So,
yeah,
okay,
bullet
thank you.
before.
Okay, thank you.
Thanks.
Any other intervention? So we thank Professor Issa Taksuba for his presentation. Thank you very much.
Qui va venir hein? Qui va venir après C'est une session. Ah, c'est une session. Vous allez utiliser votre ordi, oui. D'accord. Donc, faut... Ouais, le micro. C'est ça? Oui, le micro, voilà. Le nom? Vous avez ça? Ah, oui, mon nom? D'accord.
Alors, please, your attention, please. Look at the program. If your presentation is scheduled in Adan Sonia, you remain here. But if it is scheduled in Digitata, please go downstairs. Thank you. So another message, I wish that all those who had the IUPAC grant, just after to take a picture with the president of IUPAC and the president of FASC, just before the General Assembly. Okay? So is there anyone who can gather all the grantees? There are 8 from Senegal and 5 from the other African countries. Thank you.
Thank you. Good afternoon. I'm Professor Ziao Naoussé from Côte d'Ivoire. I am going to manage this session. In this session, I plan about seven communication presentations. And the first presentation will be made by Professor Atem Ben Ramdan. So, and the title, I think it's not projected, Improve the Safety and Security in the Chemistry Labs, Result and Action Implemented at the Faculty of Science of Tunis. Professor.
Thank you, Mr. Chairman. Good afternoon, everybody. I will not speak about chemistry, but another kind of subject who interested, the safety and security in the lab. And first of all, I would like to thank the scientific committee for giving me this opportunity to share with you some of our concerns about the chemical safety and security in our institutions, and the solution that we adopted to improve them. I would like also to thank the Federation of African Societies of Chemistry, the Royal Society of Chemistry, OPCW, as well as the Comité Sénégalais de Chimie
for supporting me to attend this event. Just one slide about Tunisia. I prefer not to speak about places and monuments to visit because you can find easily this and that information online. But I think that I highlight two important points. Tunisia is the country with the oldest and still operational university in the world, which founded in 737 and named the University of Zitouna. The second thing that last year, one of the three members of the Nobel Prize in Chemistry in 2023 comes from a Tunisian father, and his name is Professor Monji Bawendi. Now let's move on to describe the current situation regarding the Tunisian academic institutions which hold or should hold the stock of chemicals. In Tunisia, we have 7 faculties of science, 14 engineering schools and scientific and technology institutes, 11 colleges, many training centers, without taking into considerations faculties of medicine, dentistry, and pharmacy. And what I will describe next for the Faculty of Science of Tunis also concerns all these establishments as well as most of schools and faculties in North Africa and some African countries. The Faculty of Science of Tunis, where I'm working, has 6 departments. 4 of them contain chemicals in different quantities. The areas where these chemicals are used are either in teaching lab or research laboratories. But in these departments, there is also several areas dedicated to chemical storage. And these storage facilities are linked to the departments and located in several buildings in the faculty. As you can see is in this overhead view, storage spaces and buildings are geographically dispersed. Here on the right, you can see the Department of Biology and Geology. Further on, we have the Physics Department. And here we can see the Chemistry Department that contains the amounts of chemicals. On the right, you have the teaching block, and on the left, you have the research one. In addition to the chemical used in laboratories, there is a space, bottom of the picture, dedicated to chemical storage that have just been delivered by suppliers or waiting for use. One of the main problems of our chemistry department is that it contains many accesses for all floors, and these accesses are unguarded. The means to ensure the security and monitoring of storage areas often non-compliant. For example, we don't have access control devices. Doors are often unarmored and closed by a simple blockade. And compartments are equipped with simple padlocks, and aeration, ventilation, and organization systems are often absent or in insufficient number. We often assist to an easy access to the research lab during and after working hours, And this is due, among other things, to a lax control at the gate of the faculty, which often allow access to outsiders. As mentioned before, in addition to storage facilities, many chemicals are also found in teaching and research lab. This may cause internal threats, such as probability of incidents that may be due to the weather when weather conditions, especially when it's hot, or the lack of staff training, or external threats like theft or use of some dual-use chemicals to commit malicious acts. I talked about the lack of staff training. In fact, we lack qualified staff for many reasons. Since some years ago, there have been no new recruitments, and this is due to difficult economic situation, and the existing staff are mainly elderly people, close to retirement, and not motivated at all to follow training cycles. Added to this, there is no awareness of standard operating procedures, and the budget lines dedicated to investing in an effective safety and security system have been either insufficient or completely absent. Now, regarding the storage and the management of chemicals, we don't have a central purchasing and monitoring at our headquarters. Each laboratory manages its products independently without sharing. And in general, the systems used for inventories are archaic and not computerized, making them difficult to monitor or update. The management of chemical waste is another difficulty that is encountered almost daily. This concerns volatile organic solvents and different chemicals that are often in the form of mixtures. Having said that, in recent years, scheduled waste collection and the involvement of private companies specializing for collection, treatment, and neutralization of waste have been temporarily stopped, and this was due to many tedious administrative procedures and agreements together. Faced with all these problems, we have begun to act in recent years. However, as a first step, we had to raise funds, and for this we participated in various calls, including those launched by CRDF Global as part of the chemical security program initiated by some years ago by the US Department to help some countries improve the chemical safety and security. And we were lucky enough to receive grants 2 times in a row, in addition to our participation in numerous workshops organized by CRDF Global, Sandia National Lab, with collaboration of the Chemical Society of Kenya, focusing on various aspects of chemical safety and security. Here's some example of equipment acquired with these grants: the purchase of 5 access control for 5 premises belonging to our lab, the purchase of 5 surveillance cameras with a digital video recorder. This is not for the purpose of spying on my researchers when they are working, but only to have a record in this case, in the case of malicious intrusion, or in general when problems are detected. And the DVR hard drive we can record for 30 days. This grant also allowed us to acquire 5 cabinets for chemical storage, and equip our storage space with an armored door controlled by an access control device. Another very useful tool that was developed by the Sandia National Lab for the management of chemicals has helped us to manage our and organize our chemicals. It's a chemical inventory software named CMS, very easy to use, and especially it's free to download via this link, and I highly recommend it. With all of this, many actions to be done, remain to be done. First, we have to convince the leadership to be more and more engaged for improving the chemical safety and security by proposing concrete actions. A budget line must be allocated to initiate an action plan. More training for staff, researchers and students must be provided through the organization of workshops in order to make them aware of everything that concerns their safety. It will be necessary to look for ways to recruit qualified personnel, and if new recruitment is not possible, it's required to redistribute tasks of existing staff with follow-up and training. Also, it's essential to continue to seek funding opportunities through organizations such as CSP, CRDF Global, or other sources. Security must also be increased by installing all the equipment to do so. We must use better inventory management via softwares dedicated for this and try to share these inventories to limit surpluses and reduce stocks. And provide the central purchasing, of course, if it's possible, and monitoring unit to increase the traceability. These are sample examples, some examples of actions, but there will be others to come. I would like to finish this talk by a quote of William Arthur Ward, who said, "The pessimist complains about the wind, the optimist hopes it will change, and the realist adjusts the sail." And we hope to be among the third kind of people. This is the next event, which will be held by Tunisian Chemical Society between 15 and 18 December in Hammamet in Tunisia, and you are welcome to come in your country, Tunisia. Thank you for your attention.
Thank you very much, Professor Ramdan. It's time for some questions. Yes. One question or two? Yes. Bon. Est-ce qu'il y a un micro baladeur?
Okay, sir. Yeah, my name is Adel Bidbe Sadiq from Nigeria. My question is, how are we going to manage our waste in the laboratory, which is a common question people ask here and there? That is the first question. Number two question, when you're talking about the professionalists in laboratory to work and then certified technologists or less scientists, in a way that somebody have a BSc in chemistry and then he willing to work in chemistry, sometimes there may be some conflict of interest that they want somebody that studied science, laboratory technologies, option of chemistry, not that BSc chemistry. Is there anything that is applicable or a way that organization can come up by resolving that career conflict?
For the first part of question, I think that for grants you speak, if I understand.
Laboratory, how to handle laboratory waste. How to handle laboratory waste, chemical waste that we use in the lab. Oh.
We don't have a solution now for currently because it's really a problem for us, but we hope that it will be solved soon by the ministry, by government, if necessary, to find solution because for some of them we recycle some solvents to use to wash instrumentals and some apparatus, but it's really a problem for us. And for the second question?
The second question is a question and then, let me say, a request that for some people, early career chemists, like someone that have BSc, and then they're willing to work in the laboratory, let's say chemistry laboratory, but in some organization, they prefer to take somebody that have science laboratory technologists, also in chemistry, than someone that have BSc chemistry.
Tu traduis pour moi parce que j'ai pas compris la question. La prononciation est terrible. Bon.
Oh.
No, we can speak after if you want. We can continue the discussion.
Okay. Let's say have chemistry. Then somebody have with technology, obtain chemistry. And the both of them want to apply for laboratory job as a technologist. But in some organization, they prefer to pick somebody that have science laboratory technologist than someone that have BSc chemistry. Is there any solution from organizing like this or international body like IUPAC, RSC to communicate to other bodies?
Oui. Oui. Nous, on fait de la chimie, donc je ne vois pas la question, franchement. Oui, I am polymerist and my team work on polymers. So we synthesize this product. We are near approach organic chemistry. So all the problems that organic chemistry we can find in my lab. So I prefer to hire chemists, not. Oui. Mais qu'est-ce qu'il y a un rapport avec la sécurité, ça? Bon. We can continue the discussion.
All right, thank you, sir.
Je n'ai pas compris sa question.
Il est anglophone ou francophone, lui? Sinon, il faut quelqu'un pour traduire. Hein? I think there is the translation. English. Thank you. Thank you, Professor Ramdan. Let's vote for him. Thank you. The next presentation will be made in the number S6C64.
Tu as compris, toi?
It will be made by Modou Yenge Diop. It's you? After Modou Yenge Diop, the next will be Mohamed Diop. Il est là? Mohamed Diop.
Les chimistes, vous préférez?
Oh, il est absent.
Ben, les chimistes, bien sûr, les chimistes.
The other next will be Nabuk Okon Edi. Absent. The next Salif So. Ah, everybody is missing. The other next will be Michael Aungona. Oh, okay. The number S6C68. 68. And the number S6C69, Sita Job. Thank you. Okay. I remember that we are in the presentation of Modi Yeng job number S6C64. You have 10 minutes.
Thank you, Chairman. I am Modi Nyingu Job. I am very honored to present part of my research entitled Synthesis and Characterization of Composite Oxide Covered by Polypyrrole used for the elimination of chromium equivalent in water by adsorption method. The plan include introduction, the materials, resulting in discussion, and conclusion. Introduction. The contamination of water resources represents a significant environmental challenge, which is the deterioration of water quality affecting the ability of some safe drinking water. Chromium is a heavy metal that is toxic to humans and excites in several oxidation states, of which the trivalent and hexavalent states are the most stable. Chromium hexavalent is a toxic and carcinogenic form which can also cause abnormalities that are well represented in the following figure. A variety of technology have been developed. Electrocoagulation, adsorption, excitation, nanofiltration. Adsorption is the immediate particularly promising techniques owing the ease of regeneration of absorbance, high efficiency, ecological sustainability, and promising potential. For the synthesis of oxide, we use the materials pacemaker, sealer, and balance. The solder metals have used for synthesis of oxide. This process were represented in the following in the picture. The precursor was mixed in ethanol solvent at 6 degrees Celsius. Citric acid was added to the mixture, and the water was stirred for 4 hours of high degrees Celsius until azer was formed. This was in turn dried in the oven at 100 degrees Celsius for approximately 60 hours. The salt formed was then calcined at 500 degrees Celsius for 5 hours. The pore formed was then polymerized with pyrrole as the monomer. The polymerization of oxide using the in-situ oxidized polymerization. After polymerization of this oxide, the null composite was formed. This null composite was characterized using the DRX spectra. We note the presence of the 311 peaks characteristic of the CFC structure. There is also a shift in peaks with the polymerase form indicating interaction between oxide and polymer. The morphology of two compounds was characterized using SIM. The same image further demonstrated the formation of homogeneous and individually identifiable nanospheres. These findings indicate that the polypyrrole casing is uniformly distributed around the oxide, thereby confirming the formation of polypyrrole nanosphere with robust interaction between polypyrrole and the oxide partners. The EDS spectra of two compounds are shown, while the spectrum of the polymerized form shows the presence of both of oxide and monomer elements, demonstrating the formation of the nanocomposite. After synthesizing this nanocomposite, we use the nanocomposite for removal chromium in water. The parameter of treatment, effect of contact times. 3 milligrams of absorbent is introduced in 75 milligrams liter chromium solutions, stirred at times intervals. The result have been plotted in the following figure. It can be seen that the amount of absorption increases with the time before stabilizing after 90 minutes, which shows that equilibrium is reached after 90 minutes. The study of pH variation was carried out by varying the pH. It can be seen that the amount of the absorption varies with the pH. We can see that the amount of absorption peaks at pH 2, decreasing with increasing the pH values. This shows that the optimum pH is 2. The dose of absorbent was studied. We can see that when the mass is increased, the percent of elimination increases as there are more absorption. The kinetics model. Two models were used. First order model and second order model. The plot of two models was determined the parameter of two models. In next table, we have the data of two models. The second order model is a more reliable method for describing the absorption of chromium because the correlation coefficient closing to unite. Absorption is a term where is an important parameter for determining the nature of the absorbent surface. For this study, we use three models: Freundlich, Langmuir, and Tompkins. The data are shown in the table below. It can be seen that the Freundlich model has a correlation coefficient close to unit. This shows that the absorption following the Freundlich model which testified of the phenomenon of chemical absorption. Thermodynamics parameter. For the study of temperature variance, we took two temperatures. After plotting the evolution of adsorption quantities as a function of the inverse of temperature, we see that positive values of delta H, which is greater than 20 kilomoles, confirming the phenomena of chemical absorption. The negative values of free energy indicate that the absorption of chromium is spontaneous. Wastewater contains other metals, so we studied the impact of these metals of chromium removal. The diagram shows that the cations have no effect of removal at pH 2, while anions cause a slight decrease in the amount of absorption. It can be seen that cations have no effect of chromium absorption compared to anions. This is due to the electrostatic interaction between the adsorbent surface and the various ions. Conclusion: adsorbent exerts an exceptionally high capacity for the removal of chromium ions, while a removal rate of 97% at 24 degrees Celsius and of pH values of 2. The adsorption process is dependent of the pH, and the kinetics illustrated the chemical natural of adsorption with the second order model. The temperature evolution demonstrated that the adsorption process is endothermic, thereby confirming its spontaneity. This material exerts high selectivity and excellent absorption performance for chromium ions. Furthermore, it may be used as an effective sorbent for the treatment of water contamination by chromium ions. Thank you for attention.
Thank you very much. Are there questions? A question? So, if there's no question, let's vote for him. Thank you. The next, I think, I will recall Mohamed Job, missing. Nabuk Okon Edi, missing. Salif So, missing. And now, I think Michael Aondona Iyo Renba. Yes. Thank you. C'est bon? So, Mr. Comment on dit? Doctor?
Yeah,
where is the pronunciation?
Iuhemba.
Voilà. Doctor, you have 10 minutes for your presentation.
Thank you very much. Hello, everyone. My name is Michael Yohemba from the Federal University of Agriculture, Makurdi, Nigeria. I'll be presenting my communication titled Structural Features and DNA Binding Abilities of SBA15 Nanostructures Silica-containing amino acids grafted with vanadusine complexes. Okay. Yeah, so the study of metals in biology is rapidly expanding, and is specifically the subfield of bioorganometallic chemistry. Interestingly, organometallic compounds provide a scaffold which can be functionalized and designed, and from here we will be able to get a lot of interesting materials for bioinorganic applications. These are some of the metals that have been employed in chemotherapy, especially with involving the ligands of amino acids as ligands. So those of vanadium, titanosine, palladium, etc., have been very interesting in bioorganic chemistry. But for this presentation, we focus on materials synthesized and developed from vanadusine dichloride. Cancer remains a problem whenever we mention the topic cancer, attracts a lot of attention because it is the second most common fatal illness after cardiovascular diseases, and there is need for development of new and better therapies and diagnostics. Now, metal drug nanostructural systems may be the solution. And also, the mechanism of action of metal drug are yet to be clearly understood. So the question now is DNA interaction possible target? DNA, is it a possible target? We'll see. Motivation, just for mention and comparison, nanostructured materials are materials that are in the size of the range where we highlight in yellow, in orange there, and the ruthenium complex have worked like a Trojan horse for platinum and palladium complexes. So here we think that it is possible to get a metal drug system onto a nanostructured material and send it to act just like the Trojan horse. And this is the motivation behind this research. So here we synthesize and functionalize the nanomaterials. We first synthesize the SBA, and then we functionalize the SBA with an AP, and then from there, we incorporated our amino acid, the cysteine, captopril, and penicillamine, and after which, our anti-cancer or the metal drug agent, which is the vanadocene dichloride, is incorporated to get the final material. Here is just some of the photos to show how the synthesis was done, filtration of SBA on the vacuum and calcination, and of course, functionalization, reaction setup is what we have there. So we carried out some transmission electron microscopy analysis, and results showed that there's some ordered hexagonal structure for the SBA and the cysteine functionalized system. Also characterized by powder X-ray diffraction and BET. So we can see in A there that the X-ray diffraction pattern of the SBA shows a peak at the 100 Miller index, where there's a high intensity, but once functionalization takes place, the SBA, when the AP is incorporated, the peak reduces in intensity, which shows that the incorporation takes place inside the poles of the nanosystems. Of course, we carried out the FTIR and thermogravimetry. So the decomposition pattern by thermogravimetry allowed us to know how much of the AP and AP cysteine that are incorporated into these materials. And all of this shows that the incorporation actually takes place in the poles of the nanostructural systems. And of course, the FTIR results show that some functionalization has taken place, which involves some movement of some peaks, where especially those peaks from the fingerprint region, and those of course, in the functional group region. So we also carried out diffuse reflectance UV, that is solid state UV studies. And of course, we can see that here in the spectra, that the vanadicene incorporated material show a peak that is consistent with DD transition, which shows that a single electron in the d orbital of vanadium is present there. And this also has helped to show that the incorporation has taken place. For each step, we have the incorporation taking place as shown in that figure. We also carried out X-ray fluorescence studies, and here, in particular, the most striking important point here is the metal to sulfur ratio. That's the vanadium sulfur ratio. It shows very high vanadium sulfur ratios, which implies that the interaction is not only between vanadium and sulfur in the moieties, but also from vanadium and oxygen in the moieties. We also carried out the magic angle spinning NMR, that is a solid state NMR for some of the materials. And here we show how the structure of the material, the systems are here, and we characterize them accordingly. The CP, which is cyclopentadiene moiety, is shown there, and the mass here has to do with the aliphatic carbons of penicillamine. And of course, we also carried out the NMR spectra of the vanadicene, that is the vanadium NMR. The vanadium NMR, we carried out this, and here we show that tetrahedral coordination is at play. So we can see, like I said earlier in the result of the X-ray fluorescence, if you see the proposed structure, we can see vanadium, the link between vanadium and sulfur, and so we can also see the link between vanadium and oxygen. Okay, the link between vanadium and sulfur, and that between vanadium and oxygen. It shows that which shows the high vanadium to sulfur ratio. And now, yes, this is also that's for the captopre-functionalized system. And after this, we carried out DNA, qualitative DNA binding studies. So this is the UV spectrum of free DNA. And now, after we interact the free DNA with the drug, 1 hour interaction depicts there's a massive bathochromic shift, reduction in peak intensity, which shows that there's an interaction between the DNA and the drug. There's a possibility of an interaction. And we do in 2 hours, in 4 hours, and we see that the interaction happens, but not so different from the other times. So this is also shown here. All of these are shown in this table for the DNA binding studies of the vanadin functionalized system with cysteine. So in conclusion, SBA15 has been synthesized and functionalized with 3 different amino acids, that is cysteine, penicillamine, and captopril. Incorporation of the amino acids and metallocene moiety took place inside the poles of the nanosystems. So the metallocene dichloral functionality took place via VS and VO bond formation, and also the DNA binding studies indicated a possible adsorption of the DNA on the surface of the metallodrug functionalized systems. Now, in summary, the amino acid vanadocene functionalized mesoporosilica, SBA, have promising potential for use in future chemotherapy. Now, what our team is doing is to continue further research by exploring the cytotoxic potential and effectiveness of these novel nanostructural systems in chemotherapy. These are some of our most recent publications, and some are still under peer review, and we hope to welcome them soon. We acknowledge Ahmadu Bello University, Zaria in Nigeria, TED Fund for travel grants, Universidad Rey Juan Carlos, Universidad Autónoma de Madrid, and Complutense de Madrid. And of course, my home university, my primary university of agriculture, Makurdi. So thank you for listening.
Thank you. Thank you, Dr. Imuremba. Yeah, Imuremba. Thank you for your presentation. Some question? Yes. Professor.
Thank you very much for the question. Solid-state NMR instrument in my university, no. But interestingly, I got funding to go to Spain, to Madrid, Universidad Rey Juan Carlos, to carry out my PhD benchwork. So I stayed there for 1 full year. So I was able to carry out some of this analysis there. Also got some funding from the European Union through my supervisor in Spain. So thank you.
Thank you. Other question? No? No. Thank you, Dr. Imro. The last presentation of this session is number S6C69, and it will be made by by Sito Diouf. Sito Diouf. Un problème pour... Identifié? Si tu as identifié, tu peux le montrer. Tu as une clé? So, Mr. Sito Diouf, you have we speak for 10 minutes.
Thank you, dear President. Hello, everybody. My name is Sito Diouf. I am a PhD student in analytical chemistry. And presently, I'm in the laboratory of physical and organical chemistry and environmental analysis in the Cheikh Anta Diop University of Dakar. The job that I am going to present you is entitled the contamination of those states coming from Soumbédioune Beach by the PCB 123, 167, 120, 89. The plan of our work is following us. After introduction, we will give the experimental part and the resultant discussion, and finish with conclusion and perspective. Nowadays, socio-economic activities have led the dispersion of pollution between their extraction to domestic use. Their compound, physical, organic or biological compound can reach the water, air and soil, and the majority of them can reach the sea, while they can harm the marine species. And also they can harm the human health by the sand food. That's why it's so important to study the contamination of those species. The aim of our work is to study the level of PCB dioxide content in stores coming from Soumbédioune Beach, like the PCB 123, 167, and 189. Our species is hostage. They are benthic and sedentary. Also, they feel all the particles floating in the water surface. That's why they're likely to be contaminated, and they are consumed by the population. And here we have our site. It's a Soumbédioune Beach. This choice is motivated by this beach is a receptacle for waste water without treatment. Also, it's a landing of fish products. We have to take samples for the month of July, August, and September 2021. For his month, 5 samples will be taken, transported in a plastic bag and storing before measurement. Measurement allows us to have the biometrical parameter of this species, and it's according to this table 1. After this step, the samples are drained before doing extraction. Our extraction method is a quick easy, swift, and effective, rigor, and safe. As a purification method is a dispersion solid fast extraction. And our method analysis is the chromatography complete with mass spectrometry. And the device is a thermofisher. And here we have the different kit using for this work. That analysis allows us to have the level of PCB content in osters coming from Sumbe and it's according to this table. Also, we give here the factor according to the recommendation to the World Health Organization and the level of PCB content in the osters range from 1.609 and 14.626 micrograms per kilograms. And the factor here, according to the WHO, is giving for two men, a man of 40 kilos and a man of 17 kilos. According to a man of 40 kilos, the factor is range from 0.01 to 0.03. And according to a man of 40 kilos, the factor is range from 0.3 and 0.05. And also, we have here the study of the distribution of PCB content in ostes. And we can, we usually see here that the level of PCB is more important in the month of August. And here, we have here a study comparative according the fish and ostes coming from Sumbe beach. And here also, we can see here that the big accumulation of this polyen or this compound is more important in a fish. In short, we can understand that the level of PCB found are much higher from the reference according to the World Health Organization. That's why we explain that the contamination of this species. It's also said that the ostes can be used in a bioindicator monitoring. Therefore, the compounds of the conception of the ostes make likely to potential danger for women health. That's why we can isolate it wastewater, study the toxicity, and to make a stabilization of contamination control or monitoring plant. Mainly, we can move together, work it together, namely the population, the industrial authorities, and the scientific community to getting a better solution. That's why we, according to this work, we can make a more holistic study on another species or monitoring polyen in the various species. A diversification of monitoring element, but for example, the study of the cadmium or of the POP can allow us to have or to understand the contamination of the ecosystem and to have a database of polyen. Ladies and gentlemen, I will stay here and thank you for your attention.
Thank you for your presentation, Mr. Sitor Diop. Some questions for him? Okay. Okay.
Thank you, Mr. Sitor, for your presentation. I would like to know the reason why the PCB is higher in August and the cause of the, I don't know if you tell it in English, the infestation of in Sumbejun.
Okay.
The reason why, and what you advise population or people around the economy, the activity in the plage.
Thank you, Mr. According to the level of PCB content in ostes from the month of August, we have firstly the rain season in this month of August. That's why the rain season can make more the phenomenon of bioaccumulation and explain the difference according July, September, and August. And for recommendation, we allow the population to make some study again. According we study, for example, when we study again another compound, this allow us to know the contamination of this species. And also at the end, we can recommend population to make attention for the conception of this species. Yes. 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 The rain season of yes. Coming from Simbaju. And this yes, and this is the wastewater, and this wastewater is the wastewater without treatment. Yes. They have no treatment according to this wastewater.
Another question? No? Okay, thank you. I would apologize. I announced at the end of the session, but there have somebody who was planned yesterday was missing, and now she wants to make a presentation. I am going to apologize for him. If you have a program book, you go to page 14. It's the number S2 C21. Madame Kumbagay. Madame Kumbagay, you have 10 minutes, a maximum of 10 minutes for your presentation.
Okay. Good evening. I thank you for giving me the opportunity to present my work on the subject removal of beta-blocker bisoprolol fumarate from water by electrophantom treatment. In introduction, pharmaceutical compounds that are beta-blocker are a group of polluants detected in environmental whose harmful impact on ecosystem and human health have been proven. Treatment conventional are not able to remove this compound. Promptly, the use of alternative techniques like electrochemical advances oxidation processes, which are a powerful method for removal this organic persistence in water. For this, the electrochemical advances processes are based in the in situ production of hydroxyl radical air. These hydroxyl radical air are produced directly by anodic oxidation or indirectly by electrophantom by the reaction of phantom. To carry out our studies, we quantify the degree of mineralization by the monitoring the talk with a talk analyzer. The electrolytes were carried in a 30 milliliter cylindrical glass cell. Was monitored out in 30 milligrams cylindrical cell containing solution of bisoprolol fumarate. On this condition, once the hydroxyl radical produced by the reaction function, it can be degraded the organic compound until the mineralization. First, these processes are depend of much parameters that we will be optimized. At first, we can optimize the effect of current on the mineralization of anodic oxidation. As we can see in the picture, the mineralization, the evolution of mineralization rate was following by measuring the Tox solution with electrolysis time at different cure intensity. As we can see, the mineralization rate depends on this type of anode using in oxidation, in anodic oxidation. The result indicates that anodic oxidation of bisoprolol is so much efficient with BBT anode compared to platinum anode. With the BBT anode, the mineralization reached 18.4% in 6 hours at 20. In 6 hours at 100 milliamperes. While for the platinum, the mineralization rise is only 27 milliamperes. This better performance of BBT anode can be explained by it promises the formation of high hydroxyl radical on this surface. Also, we studied the effect of current on the mineralization of bisoprolol by electrophoton, and we saw that the mineralization depends on this current appliqué. And so current appliqué, the mineralization for the platinum anode, the increasing of current also resulted in higher mineralization rate until 300 milliamperes. For the BBT anode, the mineralization rate is increasing with the current until 1000 milliamperes. Such with BBT anode, the mineralization rate existed at 98% at 500 milliamperes, while with platinum anode, it was around 18% at 1300 milliamperes. In order to find the better efficiency relative to the low cost of these processes, the mineralization current efficiency and the energy consumed are evaluated by this, basing on this equation. Based on this equation, it can be noted that the mineralization effective constant current is the mineralization current effective current is around 10%, is around 10%, and when we can notice that the energy consumed is also being around 1 kilowatt hour TOC, except in the processes oxidation anode using platinum. So the mineralization current effective and lower the constant the current the energy consumed value are obtained with anode, showing the best gratin mineralization power of electrophantom processes with BBT anode. Therefore, the mineralization performance can be classed in this order. In conclusion, the oxidation anode processes was proven much more efficient using bore doping diamond anode than platinum. Was explained by the greatest amount of active hydroxyl radical. The electrophantom processes is then much more effective than anodic oxidation with platinum. Then the optimal mineralization rate was obtained with the BBT anode at 500 milliamperes after 6-hour electrolysis. And thank you for your attention.
Thank you, Madam Gay. Some questions for her? No questions? Okay, thank you. This ends up this session. Thank you for your collaboration.
Ok, merci beaucoup.
Yeah, c'est bon, c'est bon.
Okay, sorry.
Yeah, can I have your attention, please? So we're running late for the FATC General Assembly. So what we're going to do is the talk that's supposed to be given now will be given tomorrow. So we've got 10 minutes to get coffee, and then we're going to start the meeting, because we've got people who are attending by Zoom, so we have to keep to the Zoom time. So you've got 10 minutes, the coffee's ready, go and get it, and you've got 10 minutes, and we're going to start the meeting. The AGM, not the talk. Okay, so the talk will be tomorrow, okay, because we're running late. Okay, and we've got Zoom people all over Africa who are in. Okay, thanks. Thank you. Are they connected, do you know?
The meeting is for everybody?
Yeah, anybody. Oh, yeah. And everybody is welcome to attend. It's an open meeting and anybody can attend the AGM. Yeah. Are the people online? Could you just tell them we're going to be 10 minutes late? If you could just send them a
Yes, no.
thank you.
That's why. Everything is cool. Everything is cool. PM that is Kadakenme. That one. Ask whether his laptop is being processed for repairs of. Which repairs? And the laptop that she was using. I don't understand now. His laptop, the laptop that she was using was faulty. Was faulty. Yeah, so we requested for compliance to repair it. I tried to trick you with respect, but it appears that doesn't matter. Do whatever the
So, okay. Or if you prefer, we just delete it. We just delete it. Okay. And the highlights.
Right, we're going to start the meeting. So I'm going to close the doors so we don't get noise. But if you want to come. Yeah. Okay, so welcome all to this 9th AGM of FASC, and it's a pleasure to have you all here. I'm going to act as the facilitator, and the FASC exec is sitting in front of you. So they're the ones who run the FASC show. So basically, I'm going to pass over to them, and they're going to give their various reports during this session. So it's a standard AGM General Assembly that we need to undertake. So with that, I'm going to pass over to our President, Professor Gloria Oberteur, who's going to take over from here.
Well, good evening, everybody, and I'd like to welcome all of you, all of us, to the 9th AGM of FASC. Today, at Radisson Blu Hotel, Senegal. I know that has been an interesting session. This was not in here from Monday till today, and this meeting will be brief, because I know most of us are quite exhausted. You're all welcome. Any apologies from any of these countries? Apologies? Clarence, anybody send apologies to you? No apologies received. No apologies received. Thank you very much. I believe that the relevant people have the agenda. You have the agenda with you. I'd like a confirmation that you have the agenda with you. Is there any